Okay. So a very good afternoon to one and all present here. Welcome to this session 11, day 6 of the AICT sponsored Atal LTP program. So today we have with us a very well-known speaker, Professor ML Kole sir from University of Ashdar, Norway. So Professor Mohanlal Kole sir is a full professor of smart and sustainable electrical energy system with renewable and hydrogen at University of Agder, Faculty of Engineering and Science in Norway. Just a second, everyone. Okay, sorry for the interruption. Sir, a globally respected renewable energy technologist, he brings over 3 decades of international academic leadership, having held esteemed positions at world-renowned institutions such as University College London, UK, Australia, University of Dundee, UK, and University of Jyväskylä, Finland, Hydrogen Research Institute, Canada, and others. Professor Kole was a key member of South Australia First Renewable Energy Board 2009 to 2011, where he contributes to the development of pioneering renewable energy policies. In the recognition of his vast academic contribution, he has been offered the senior leadership roles, including Vice Chancellor of uh, Homi Bhabha State University, Mumbai, India, and professional chairs in sustainable engineering and smart grid technology at Teesside University, UK, and NTNU, Norway. A dedicated forwarding educator, Professor Kole has taught a wide range of advanced courses in electrical and renewable energy system, hydrogen technology, smart grid, and energy economics across leading universities in Europe, Asia, and Australia. He has mentored numerous PhD scholars, and including many engaged in industry-sponsored research, bringing academic knowledge with real-world energy solutions. Many postgraduate projects under his supervision, conducted in close cooperation with industry, have, have been recognized with Best Thesis Award. Professor Kole led and secured competitive research funding from prestigious institutions such as European Union, Norway Research Council, EEP, SRC, BPSRC, NRP, support cutting edge in sustainable energy technology. His research excellence is demonstrated by H index of 30, I-10 index of 114, an average of 2,000 to 250 citations for each of his top 10 publications. Dr. Gole consistently ranked among the top 2% scientists worldwide by Stanford University based on Elsevier data since 2020. Professor Kole continues to be a drive force in global efforts towards clean energy transition and influencer, researcher, policy advisor, and academic visionary. So, welcome, sir. Welcome for this FDP and accepting our invitation, sir. Over to you, sir.
Yes, thank you, for giving such a nice introduction. And thank you very much for giving me the opportunity to share some of my knowledge in this AICT-sponsored faculty development program. So I use the share screen, and then you have to help me. Shall I use window or entire screen?
You can use entire screen, sir.
Entire screen, okay. If I use window and then I make the full screen mode, then it works, or how it works?
Basically, it works in both modes, sir, but it works better.
Okay,
on the
ultra.
entire
Okay. I put the window. Now, can you see the window?
No, sir, not yet, sir. No, no, it is visible, sir.
Not it?
No, no, it is visible, sir.
Okay,
It is
I'm
visible now, sir.
stopping. It's visible?
Yeah, it was visible, sir.
Okay, I'll try. Then let me see. I stopped. Yeah, a window. Share. And if I make a full screen mode or presentation mode, is it coming now? No,
Yeah,
not this
okay.
one. Just a minute, just a minute. I missed a long one. Right. Now it is coming in the full screen mode.
Yes, sir. Yes, sir. Yes, sir.
It's full screen mode, right?
Yes, yes, sir.
Very good. So, thank you very much for giving me this opportunity to share some of my knowledge or experience for working of sustainable electrical energy system with the participants. So, uh, today, I would like to talk with you regarding the microgrid. And as all of us, we know that Government of India is promoting solar photovoltaic system through various schemes like PM Surya Ghar Yojana and many other schemes, in which the focus is that how we are going to integrate the solar photovoltaic system. We have observed that in most of the cases, these solar photovoltaic system are integrated within the distributed energy system. When we are connecting the solar photovoltaic system within the distributed energy system, as an engineer, we know that in future we are going to have a lot of technical and operational challenges. When we are having the solar photovoltaic system, let's say the roof mounted on the houses, then it may not be possible to have proper interconnection and energy management of the solar photovoltaic system. To have the proper energy management, including power management, it is very essential to integrate these photovoltaic solar systems with appropriate energy storage as well as distributed generators or dispatchable distributed generator, and then developing appropriate power and energy management strategy. We can work as a microgrid, and such type of microgrid is going to help us in increasing the penetration of solar photovoltaic system within the distributed network. That is the high level information for today's lecture. In today's lecture, I would like to share my experience of working on one project, and that project is mainly based in your area. It was Gurugram area where the TERI, the Energy Resources Institute, have been located, and we developed the microgrid integrated with solar photovoltaic system, energy storage, and dispatchable distributed generator. And then we provided the energy management strategy, power management strategy, including techno-economic sizing by taking into account the local energy pricing dynamics. So the outcome from this lecture or from the project, which was funded by basically the Norwegian government, is going to be very useful for all of us. Right. So I have given you a little bit motivation why we need to work on solar photovoltaic based microgrid. And here, the objective is that when we are trying to have solar photovoltaic system, and in this case, we have taken the institutional system, because we know that if we are going to take the institutional system, in institutional system, it is very easy to control the load as well as to integrate the dispatchable distributed generator, energy storage, and to make the proper energy and power management planning also. So the objective here is that if we are taking the institutional energy system, and in the institutional energy system, we are targeting to have the solar photovoltaic system. And of course, that is going to be limited due to the availability of space. So how we have to do the technical and economical sizing of these solar photovoltaic system, energy storage, distributed generators, by taking into account the conditions of critical and non-critical load. And of course, when we are talking about the economics also, then of course, not only the capital investment related to the solar photovoltaic, energy storage, or dispatchable sources are going to be taken into account, but also the market energy price dynamics are going to play the major role. So all those factors have been taken into account in these objectives. Then accordingly, when our objective is to develop the microgrid with having the key focus of solar photovoltaic system and making more energy throughput for the local resources and considering the market dynamics, then of course we need to do the proper work plan also. That also I am going to share with you. And on top of that, the first thing which is a very important is that techno-economic sizing of institutional photovoltaic based energy system, in which I mentioned earlier, not only the technical and economical parameter, but also we need to take into account the typical grid outage conditions of our Indian distribution system. And that also we considered in this one also. And then when we have the appropriate sizing, taking into account grid outage condition, critical load, non-critical load, market energy pricing, market dynamics, then we have all this sizing, right? Then we need to develop appropriate energy management strategy for doing the effective operation of photovoltaic based microgrid. And then when we have such type of system and we develop the energy management strategy, we need to work that how this energy pricing dynamics, which is going to change in the future due to the geopolitics and due to many other factors, how the performance of photovoltaic based microgrid is going to be there. That also been considered in this project. Then of course, the solar photovoltaic system which we are considering at a particular location, it is going to have a different operation at different geographical location, and accordingly the techno-economic sizing, energy management strategies, and energy pricing dynamics are also going to impact. So that comparative analysis also it has been considered. Then another very interesting point is that when we are talking about integrating the solar photovoltaic system within the distributed network, so we have to work on that how much hosting capacity is going to be there, and that hosting capacity, how it is going to impact the voltage quality and other technical parameters, and how we have to mitigate them within that particular distribution network for increasing the photovoltaic hosting capacity. That also have been considered in this project. And then I'm going to provide you the conclusion. So the motivation is that we want to have the microgrid, which is a group of interconnected loads and distributed energy resources within the clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid. A microgrid can connect and disconnect from the grid to enable it to operate in both grid connected or island mode. So this point is very important. And considering this point and considering the typical grid outage conditions within the India, a photovoltaic based microgrid for Gurugram have been developed and operated under this project. So here, the objective is that we need to have a very reliable energy system in which we are going to have the solar photovoltaic system. And this solar photovoltaic system, when operating as a microgrid, we have to see the energy storage and distributed generator. So it should work like a decentralized, distributed, digitalized, decarbonized, and diversified. So now, to develop the reliable and efficient and of course cost effective microgrid, we need to work first on developing techno-economic sizing. So considering the techno-economic sizing and getting that, we need to work on its operational performance. Based on the operational performance and taking into account the critical and non-critical load conditions, we need to work on energy management strategies. When we develop this energy management strategy, of course, it is going to be impacted by the market energy pricing dynamics also. And of course, this microgrid in which the solar photovoltaic system is a key element, then it is going to have the impact of meteorological parameters that also we need to consider. As we know that due to the climate change conditions, solar force radiation patterns, they are all changing also. And of course, we know that within the distributed network, we have some grid constraints also. So first objective, what we considered here, how we have to do the techno-economic sizing of photovoltaic based grid connected system to operate as a microgrid with anticipation of frequent grid outage condition to supply the reliable power. The second objective, which we considered here, development of photovoltaic based microgrid operational energy management strategy with minimization of energy generation cost of local resources with local energy throughput. Then to maximize the local resources energy utilization through appropriate energy strategies by enhancing local energy storage, participation with consideration of grid constraints. Then we considered the objective to improve the operational performance of institutional photovoltaic based energy system by reducing the grid dependency, and then impact of market electrical energy pricing on operation of photovoltaic based microgrid. So these key objectives have been covered. Then of course, I mentioned earlier also geographical location and local grid constraints are also going to impact the technical and economical performance of photovoltaic based microgrid. And of course, the local energy market price also going to be there. And then we know that at different location, due to the distribution power network capacity, the PV hosting capacity is going to be very different also. That also have been considered in this project. And then considering all these factors into account, the operational performance analysis, for example, the voltage quality, line loading within the network with reference to the increasing PV penetration have been analyzed. And of course, then we also addressed some of the mitigation techniques in which how we have to include the reactive power versus voltage drop characteristics in the power conditioning devices for improving the voltage quality within the distributed network with increasing PV penetration. So you can see that in this project, lot of objectives have been considered. So based on this objective, the work have been divided in different plans. So let's say work package 1. How the work package 1 it was discussed. In the work package 1, we did the literature review for identifying the research gap with reference to the microgrid which we want to develop, considering the objectives which we did, which I have defined in the earlier slides. So with reference to the work package, the state-of-the-art literature review and the research gap which have been identified, and they have been published in these 2 IEEE articles. If you are interested in understanding the how the research gaps have been identified with reference to this project, right? I request you to refer these to IEEE articles in which you will get the idea that how this research gap with reference to our Indian condition and especially with reference to the Gurugram institutional energy system, how we have to work on that one. So after identifying the research gap, when we move to the next work package, in next work package 2, the key objective, it was techno-economic sizing, and then developing the energy management strategy and doing the performance evaluation. So this objective or this work package, it was very interesting, and the outcome from this work package 2 have been published in Elsevier journal, which DOI have been given here. And if you are interested in understanding that how the techno-economic sizing have been developed, and then how the energy management strategy have been proposed, and then based on how the performance evaluation of the system by considering the energy resources condition at the Gurugram, that have been reported in this article. And if you are interested, please refer that one and feel free to utilize the results or the outcome from these articles for your research work or even for your teaching also. So that was really interesting. So then we moved to the work package 3. In work package 3, the focus was that how we had to develop the energy management strategy. And in that energy management strategies, we considered the market energy pricing dynamics. So here in these conditions, the typical Gurugram area energy pricing dynamics, annual energy pricing dynamics have been considered, and based on that, the performance evaluation have been reported, and the technical outcome from this work package 3 have been published in Journal of Cleaner Production. DOI has been given there. So if you are interested, you can go through this article, and most of these articles, they are the open essays, so you don't need to worry about the subscription, and you can download them, read them, utilize them for your research work. So here you can see that in this article, especially related to the work package 3, how the market energy pricings are going to be impacting the performance of microgrid, in which the focus is to have the maximum solar photovoltaic system participation. And then you might have seen that we have considered the typical grid outage conditions of India also. So due to that, how the critical and non-critical load have been fulfilled, and how the energy storage and the distributed generators, they are taking into account during the grid outage conditions, and how we have to do the minimizing the economic cost of the system. All these technical details have been published in this article, and they are available there. And you have to keep in mind, when I'm talking about the grid outage conditions, so we consider, especially within that institutional system, critical and non-critical load configurations also. Then we move to the next work package. In next work package, the focus was that how this microgrid can be used for peak demand saving and doing the grid constants and doing the sensitivity analysis. And that sensitivity analysis work with reference to the peak demand saving and with reference to the grid parameters have been published in Journal of Energy Resources, right? And it's my mistake, it is published now, it is not under review, so I should have removed that one. So that article now, it is available in two. One is in IEEE, and then another is in Journal of Energy Resources also. So if you are interested that how the microgrid can be used for the peak demand saving with reference to the grid constants and with reference to the sensitivity analysis, that have been reported in work package 4. And out of that, you can see here 2 publications are reported. So now we know that the time is limited, and here I don't want to go in much more technical details, right? But here my objective is to motivate you to work on solar photovoltaic based microgrid in which we can contribute towards the government of India's vision for making us more self-reliable into the energy resources also, and promoting the solar photovoltaic system, for example, through Prime Minister Surya Ghar Yojana, Kusum Yojana, and so on and so forth, right? So all these uh, outcomes from these published works are going to help all of us in achieving the key objectives of government of India, not only of the government of India, but for all over the world, because we want to reduce the CO2 emission. And as we know that most of the countries, they have agreed that by 2030, they want to increase the 3 times renewable penetration. And most of the developed countries, they agreed that by 2050, they want to be the net zero. And India has agreed that by 2070, we want to be the net zero. So of course, then we have to work very hard, and then we need to train and educate our next generation who can contribute towards this sustainable electrical energy system. And to have that contribution more at the ground level, I believe that some of these publications, which are more or less related to the Indian system, are going to be very useful for our next generation to take this work forward. Then we come back to the work package 5, because we know that the geographical parameters, local grid constants, and local electricity market energy pricing are going to be impacting the operation of the microgrid at different locations within India also, because India is a very big country and we have the different type of grids or grid limitation at different places. So one study will not be useful for all the locations. So of course, then we had to consider, for developing the microgrid at a particular location, how we had to consider the local geographical parameters, local grid constants, local electrical energy pricing. So all these factors have been taken into account in work package 5. And out of that, a very interesting article has been published in Renewable Energy, and DOI has been given. So if you are interested to extend this work, in where the main focus, it was on institutional energy system at Gurugram, but when we want to have the wider applications of the microgrid, then I believe that the outcome from work package 5 is going to be very useful for that. And then the work package 6, in which different penetration impacts of solar photovoltaic system with reference to the voltage quality, hosting capacity analysis, that have been considered in work package 6 also, but taking into account the typical grid condition. And that work has also been published in Springer Nature Applied Sciences. So it is not under review, it is published now. My apologies for writing that under review here. So here you can see that with reference, when we are talking about a simple solar photovoltaic based microgrid, and when we want to integrate all these things together, considering the grid outage conditions, so how we have to make a work plan, and based on this work plan, how we have to do the more detailed research, and not only getting the research also, but helping the distribution network or the energy policy makers also getting it implemented within the field. That is going to be our key objective. And getting the implementation of the microgrid with reference to the solar photovoltaic system, right? Of course, we as an academician, we can educate and train the next generation, and that next generation professionals can help in implementing such type of system within the distributed network. And then, of course, the conclusion have been covered from all work package in work package 7, and then how we need to. So here in the previous slide, I have given you a very good idea that how we have to integrate different work plans together right? So considering all these factors into account, now I'm going to share with you energy management strategy with reference to the techno-economic assessment of photovoltaic-based institutional microgrid. So now this is based on the article in which the detailed technical results have been reported. So now, with reference to this point, the key objective is that how we have to get the techno-economic sizing a photovoltaic-based grid-connected system to operate as a microgrid with anticipation of frequent grid outage condition for supplying the reliable power within the microgrid. So here, the objective is that we need to find out appropriate sizing. To get this appropriate sizing of photovoltaic-based grid-connected microgrid, we need to consider appropriate technical lifetime. Let's say if we have the technical lifetime of 25 years, for example, within that 25 years of technical time, we need to consider the market inflation, dynamics of energy pricing with reference to the next 25 years. And not only from that point of view, but we know that every technical component is going to have limited technical lifetime also. This technical lifetime of the components which are going to be integrated within the microgrid are going to depend on its technical and operational performance also. So due to their operational performance, their technical lifetime is going to be changed, and that due to that, there is going to be a number of replacement of the system components are going to be there within this specified technical lifetime of the project. So those factors have been considered while calculating here the techno-economic sizing of the photovoltaic-based microgrid system components. So you can see that it is not that easy. For example, if you are considering the batteries also, and of course the batteries are going to be the key part in the microgrid. So the performance of the batteries are going to depend on its charging discharging cycles, loading patterns also, and then of course the battery technical characteristic also. Based on that, we need to calculate the battery's technical lifetime also. And that battery's technical lifetime within the 25 years of time, for example, like how many number of replacement of the system components of the batteries are going to be there. So that calculation has to be done with reference to the technical performance also. So to get that technical performance for the sizing, we need to do all these analysis also. So those analysis have been considered in this article. And if you are interested to go all this technical detail equation, please refer this article. Then another very interesting thing is that when we want to operate such type of microgrid, so our objective is going to be to have the minimization of the generation cost with maximum utilization of local energy resources. And how it is going to be possible? With battery participation. So here, the objective of the battery is that to utilize the maximum utilization of local energy resources to go through the energy throughput through the battery. And then based on that, how we have to develop the energy management strategy by minimizing the cost of generation. That factor also has been taken into account. Now here, I've just give you a very simple case. So here, and this is the real example, right? Here you can see we have this Gurugram location here, and we have taken the institutional energy system of TERI, which is located at this location. And that at this point, or when we started the project, so we know that the load which is going to be integrated at this institutional system, there is essential load and non-essential load. And of course, to fulfill the essential load during the grid outage condition, we need to have the DG, and then the DG was there. So if we consider here, you can see that how the total and essential load, they have been distributed here. Okay, total load and essential load. And here it has been taken into the per unit values, but the real values have been reported in this article also. And here you can see that how the typical variation of the load or the load curve with reference to the time or the day of the week have been reported. Now, here, objective was that we want to operate this institutional system, right, by integrating the solar photovoltaic system and energy storage and reducing the dependency of the distributed generations with reference to the fulfilling the essential load, and especially during the grid outage conditions. So that with reference to that, how we can make a relative comparison that have been reported. So let's say if we consider only the grid and the distributed generation, so to meet the institutional demand, right, from the grid, it was 87.3% and 12.7% it was from the DG with reference to the annual contribution. But now when we are trying to have the techno-economic sizing of this institutional photovoltaic system by integrating the solar photovoltaic system and the battery bank, so then when I explained all the procedures earlier and taking into account these load conditions here, the battery capacity which has been calculated, right, it was 120 kilowatt hour battery bank, right, and then 30 kVA DG to meet the local load demand during the grid outage condition. And PV capacity, it was fixed to 50 kilowatt peak at latitude T because the limited area which was available there. And based on that, when we do further analysis, then you can see that with the objective that we want to utilize the maximum energy resources locally, that means battery energy throughput, amount of energy that cycles through the storage bank in a period. And how it is defined as the change in energy level of the storage bank measured after charging losses and before discharging losses. So that energy throughput has to be maximized. That was the key objective here. So with reference to that, then the energy management strategies for operating this photovoltaic and battery-based grid-connected system with minimization of the energy cost approach have been used, and the formulation have been given here in this equation, where the grid power purchased from the grid at a particular time, and we know that at a particular time, the pricing is also going to be different. Duration at that particular time, how much photovoltaic power is going to be there, and of course the PV energy generation cost also, that is going to be very different. Then of course during that particular time, like whether battery is charging or discharging depending, so the battery energy cost is also going to be different depending on the market energy pricing, grid, photovoltaic, and the battery cost also. So all these factors are going to be there, and then there may be the situation that we may sell to the electricity or we may buy the electricity. So that time, how the pricing is going to be there, that is also be there. And of course we are taking the grid outage conditions, and in the grid outage condition we may not have the sufficient battery capacity also to fulfill the essential load. So DG is going to be operated. So of course the DG cost, energy cost is going to be different, and the duration is also going to be different. So during that particular duration time, how we have to minimize the operational energy cost of that microgrid is we need to get minimized. That factors have been taken into account, and then different constraints. Of course, the constant is going to be with reference to the distributed energy resources, grid outage, and output from photovoltaic array, energy storage, power from the DG, all these factors into account. Then based on that, then here, the flow chart for the energy management strategy for the photovoltaic based microgrid have been explained here. So I'm not going to go in much more detail here, but if you refer that article systematically and peacefully, you will be in a position to understand that how this energy management strategy of the photovoltaic based microgrid, in which we have the energy storage also, distributed generator also, and of course the grid connected and the grid outage conditions also. So all those factors have been taken into account in developing this energy management strategy, and this energy management strategy have been explained in that article in a very systematic manner. And if you are interested, you can refer that. But now let's come to the results, right? So let's say here we are going to make the comparison of this energy, institutional energy system without and with PV and battery integration. So now here we are taking the earlier case and with the case in which we have the photovoltaic and battery. So here you can see that energy from the grid have been given in the upper graph, and energy from the DG that have been given in the per unit basis have been given here. So now here you can see that in another graph that how the energy from the grid have been changed with reference to that microgrid in which photovoltaic and battery integration is there. And then another very interesting thing, you can see that especially from the contribution from the distributed generations, when we have the case A in which we don't have the microgrid, but we have the DG for supplying the essential load during the grid outage condition and other typical situation. But with reference to the photovoltaic and battery integration and taking into account the technical and economic sizing and utilizing the energy management strategy, which have been explained in the previous flow chart or in the previous slide, you can see that how the energy from the distributed generator have been reduced drastically, right? So you see that how the local energy throughput with reference to the photovoltaic and battery based microgrid is improving, right? And how the grid dependency is also reduced. That is a very, very interesting to see in a very simple case, which I have explained here, right? And these are the typical real results from your area, Gurugram. And I believe that your university is also located in that region. So personally, I feel that if you are interested and some of the outcomes from these results, if you are implement in an institutional energy management system, how drastically you can reduce the energy consumption, not only from the grid, but from the distributed generators, and effectively contribute in local energy resources utilization, also in which we have considered the typical grid outage conditions of that area and typical market energy pricing dynamics of that area also. Now here you can see that in case 2A, right, which is without PV and battery. So grid, it was supplying 83.3% and 12.7% was from the DG, but with PV and battery integration, you can see that photovoltaic is contributing 48%, and grid, you can see that it has been dropped from 83.3 to 51%, and where the DG contribution, it was 12.7, it reduced to only 1% by utilizing the energy management strategy, which have been presented in earlier slide, right? So here you can see that how the significant contribution we are making by using our institutional energy system, by utilizing photovoltaic system, energy storage, and of course we may need a DG also because we have the typical grid outage conditions in India, how we are contributing in reducing greenhouse gas emission, or maybe in a simple way moving towards the net zero and reducing the grid dependency also. So this is a very interesting results from here. So now moving forward, so if we make a relative comparison of the energy contribution with reference to the each month. So you can see that because we have very tropical conditions and due to not that much variation of the solar radiation throughout the year. So you can see that energy from the PV throughout the year is almost remaining the same, not that much big variation. And energy from the grid is also getting reduced. And energy from the DG, especially when we have the reduced PV consumption and maybe other conditions depending on the load parameters and so on and so forth. So energy from the DG is drastically reduced. And then interesting point is the battery energy throughput to generation, right? So that is really, really interesting here, right? So battery energy throughput is a very important analysis for utilizing the local energy resources. And of course, the load, average monthly load, have been given in this year. So here you can see that the DG energy contribution is drastically reduced. Okay, battery energy throughput throughout the year is varying from 21 to 43%. PV energy contribution is between 41 to 59%. Grid energy contribution, if we take the month wise, 40 to 58%. And if we go the back, hello, are you able to hear me? Hello.
Yes, sir.
Yes, sir. Yes, sir. Sir.
Yes, sir. Yes, sir.
You're audible, sir. You're audible, sir.
Yeah, because sometimes it happens, I'm speaking and the connection is lost. So yeah,
I'll let you know if something happens, sir.
Thank you. So here I have given a very simple example, right? A real example, I can say, a real operational example, which may help, right, to all of us to utilize such type of system for teaching our end generation professionals, educating them, and not only to the students also, but also to the policymakers also, professional engineers also, right? So if we move to the system in which we have the photovoltaic and battery, so how drastic energy consumption is going to be changing. So now with reference to the performance comparison, right? So now the values have been given here. So annual grid contribution, right? Value of the microgrid, 48%, right? So with reference to the without grid, right, 45% reduction. That is quite interesting. And of course, the PV contribution is 51%, right? So in for case 2A, in which we don't have the PV, but battery energy throughput, you see 33%. That is quite interesting. And annual energy sold in this typical photovoltaic based microgrid is 4%. So that is not quite high, I can say, but our objective was to make it more self-sustainable, right? So annual grid electricity bill, right? It was calculated based on our Indian energy pricing. And for this, especially for this microgrid, with considering all this typical institutional load, right? So 45% change, right, in the annual electricity bill. So that is quite interesting. And then another very interesting thing, because we are interested in reducing CO2 emission or moving towards the net zero. So you can see that in earlier case, when we have the distributed generator, and let's say the distributed generator using conventional fuel, and then when we are integrating photovoltaic and battery, and then you can see that 93% reduction into the fuel consumption of the DG also. That is a quite high, right? So we are significantly contributing towards the local CO2 emission reduction by integrating solar photovoltaic and battery. So the key output from this is how this techno-economic sizing should be done, how we have to develop the energy management strategy, and how that energy management strategy can help in reducing the grid contribution from grid, distributed generator, and achieving drastic reduction into the annual electricity bill also. And this photovoltaic based microgrid has a big contribution right? So now that is another very interesting point. So in all these calculations, you have to always keep in mind the cost of the photovoltaic batteries, DGs, and other system components. They have been taken into account. They have not been ignored. And not only the initial capital investment, but the replacement of the system components over the lifetime of the system, that also have been considered here. So with reference to that, if we consider over the technical lifetime of the project, let's say 25 years, so then here you can see that, so battery cost was 11%, solar PV cost 10%, DG 4%, and system converter cost 3%. And of course, the grid is also integrated there. So we cannot ignore the grid cost also, because we are going to buy the electricity from the grid also, that also need. So that has also 72% contribution. So all these factors are there. Okay. So it is very essential, right? Or it is very important to consider the economic viability also, because whenever we want to have any institutional energy system, everyone is interested that how the energy cost saving is going to there, how much capital investment is going to be there, operational cost, system replacement cost, and everything is there. So here you can see that for a particular this system, 50% of the initial capital cost came from the solar photovoltaic, okay, over the project lifetime, which we had taken 25 years. And then the solar PV cost has only 10% share of the net present value of the microgrid system, right? So initial capital cost is different, but if you consider the net present value of the complete system, so it is coming only 10%. So that factors also we need to consider, and we need to explain to our students or to the policymakers or the professional engineers also, for doing all this technical and economic analysis also. So it economically viable operation is going to depend how we are calculating appropriate sizing of the batteries and the DGs. Because for the photovoltaic, we know that then it may be limited due to the available area also, and of course the market energy pricing. So these are the key outputs. Are you able to follow now? Now we move to the next point. Next point is also very interesting. So next point is that photovoltaic based institutional microgrid is there. Its technical and economic performance are going to be depending on market energy pricing. Let's say we did the sizing as we discussed in the previous article, but its performance is going to be varying with reference to the energy pricing. So with reference to the market energy pricing, how we have to develop energy management strategies for operating such type of photovoltaic based microgrid. And this energy pricing dynamics and participation of local energy resources through photovoltaic, maximizing local energy resources through battery energy throughput, having some contribution from distributed generations, and this energy pricing dynamics, because it is going to be the grid connected, right, going to impact the microgrid generation cost also. And to maximize the usage of local energy resources through battery throughput, considering grid constraints as well as grid outage, earlier I also mentioned. So those three objectives have been considered in this article. Okay, so if you are interested, right, you can refer this article and understand how these three key objectives have been analyzed with reference to the typical microgrid located at the Gurugram. Okay, with reference to the market energy price. So here we used time of use tariff. Okay, and you can see that with reference to the time, energy pricings are going to be changing. So we are not going to be taking much more interest in that one, right? So that is going to depend on the market, how the utilities they are designing the energy pricing with reference to the time, whether it is a static or real-time pricing or variable peak pricing or critical peak pricing. Now here you can see that this is from DHPV in India, and how that time of use tariff from October to March and from April to September that have been taken here in this analysis. So these are the typical electricity tariff using the values from DGPV in India, right? Because for this Gurugram area, I believe that it is the supplier or the utility company, and they are using this tariff mechanism, right? And now with reference to that, here you can see that how this time of use tariff, right, with reference to the month of year, right, they have been considered. So here you see time of use tariff 100%. We consider if it is increased to 125%, 150%, 175%, 200%, then how it is going to change. And that sensitivity analysis have been considered in this work also, right? So here you can see that time of use tariff with reference to the different conditions, let's say 100% to 200%, if it is changing, and that is going to change in the future also, right? How? And then time of use of the year also, right? That with reference to the different months also that have been considered here. Now, with reference to that, when we want to develop this energy management strategy for photovoltaic and battery-based grid-connected system with objective that minimizing the annual energy cost, okay, annual energy cost minimization approach. And for that, you can see that here the different factors, right, have been taken into account. For example, power purchase from the grid, time of use tariff is going to be there, okay, time interval, photovoltaic power output, energy generation cost from the PV, battery charging from the battery, and of course the energy generation cost of battery is going to be different, right? So all these factors have been taken into account. Similarly, the DG cost also, right, and time of the use during that particular annual year, right? Because we have to take the annual energy cost minimization approach for developing this energy management strategy. So for that energy management strategy, in which the key objective is minimizing the annual energy cost, right? So all that, taking this formulation into account, the flow chart have been developed. In this flow chart, the key point was that how we had to use time of use tariff also, that have been taken into account, okay, and then different factors, those have been considered here. So I'm not going to explain all these points here, but if you are interested, you can refer this article and go through this flow chart and try to understand that with reference to the energy pricing, right, how the photovoltaic energy storage, distributed generations, how they are operating or how their operation have been utilized. So considering all these factors into account, now here some of the results have been reported. Results of microgrid without and with energy management strategy. Results of microgrid without and with energy management strategy. So here, distributed generation and state of charge without energy management strategy have been reported here. Okay, so battery associates and energy from this. But if we implement the energy management strategy, which have been we discussed in the earlier slide or provided through the flow chart, you can see that how the variation, right, especially from the batteries, are increased with drastic reduction into the energy from the distributed generator. So here you have to keep in mind, distributed generator means not the solar photovoltaic, but the dispatchable distributed generator, which was connected, which have been explained in earlier slides also. So here, very systematically, you can see that when we are using this tariff variation, right, how with reference to the tariff variation, taking into account the time of the year, right, you can see that the energy from distributed generation is drastically reduced, and how the battery state of charge are varying. It means that energy throughput through the battery is increasing, right? And that is going to help us in understanding why we need to have appropriate energy management strategy. So here you can see with reference to the month of the year, right, with reference to the month of the year, right, so the solar photovoltaic generation is there, okay, energy throughput is there, and then this is the energy pricing, which is going to be vary, right, grid purchase rate, right, how it is changing, right, and this is the energy from the grid, also battery energy, basically it is going to depend on the solar photovoltaic and the loading conditions also, and then charging, discharging both, so that's why it is going to be the negative. So here you can see that with reference to the market energy pricing, how the energy from the grid is changing. With reference to that, how the energy throughput through the battery is also changing. That is a quite interesting to see when we are implementing appropriate energy management strategy. So with reference to without and with energy management strategy, you can see here some of the result. If we are making the system without energy management strategy, annual grid contribution is 40%, but with energy management strategy, 45%. Annual DG contribution with appropriate energy management strategy is reduced to 2%. PV is, we cannot change that one. Battery contribution, you can see, right? Battery energy throughput is increased a lot with appropriate energy management strategy. Energy sold to the energy, sold to generation to the grid is like, it's not that much changing. Annual bill is having this 1.13 to 1.1. But here, with appropriate energy management strategy, we can have the increase in the battery energy throughput. It means that we are utilizing more local resources for local supply. So with reference to that, you can see that cost of energy, right, how it has been varied with reference to the time of use tariff also. So if you use the battery energy throughput, right, here, you can see that this is the battery energy throughput and this is the cost of energy. So this cost of energy is going to have the bigger impact with reference to the time of use tariff also, and then of course on battery energy throughput also. Then if we take the this case 3C, right, then here you see how COE and battery energy throughput is changing. with different grid selling price. So here we have considered only time of use tariff, but here we consider the selling of the grid, selling of the energy to the grid, and how it is going to impact also. So in future, as we know that the selling price from the photovoltaic systems are also changing, and those selling price depends on the government policies also, how the government policies are going to be developed, right, for promoting the solar photovoltaic system and selling the pricing from the local microgrid to the main grid. And with reference to that, you can see that how we can, how the cost of energy of the system is going to be changed and reducing here, right? So that is a very interesting thing. Cost of energy increased by 71.6% in case 3B. Okay. When the time of use energy price changes from 100% to 200%, right, for selling the price to the grid. Okay. And then next point is interesting finding here. 8% reduction in the cost of energy has been observed when the selling price to grid has increased from 100%, right, to 200% at time of use price that have been kept constant at 100%. So overall, right, all these factors, right, all this sensitivity analysis which we can do for finding out the appropriate windows, right, when our system is going to be interesting. So here objective is that how we have to consider this energy management strategy with time of use tariff also, and for that how we have to work on energy cost minimization approach. And here in this article, especially the interesting thing is that we have taken the typical energy pricing conditions from the Gurugram area. That's why I thought I will share with you this work, right? Because this work is related to your area. And then we did some more sensitivity analysis on impact of PV, battery, and fuels cost on the cost of energy also, because we know that with reference to the market dynamics, photovoltaic cost, battery cost, and fuel cost, which is going to be required for the DG, are going to be vary, and that factors are going to impact in the cost of energy also. So here you can see that variation, and all these points have been explained in much more detail in that article. If you are interested, please refer that one. Okay, so here you can see that when the photovoltaic cost, battery cost, fuel cost, how they are impacting with reference to each other. Okay, so the key outcome from is that appropriate operational energy management strategy plays a significant role to achieve maximum utilization from the distributed energy resources and battery energy storage under dynamics of market energy price. With proposed energy management strategy, annual battery energy throughput has increased 0.4 to 10%. That is a very key contribution. And the DG contribution has decreased from 7% to 2%. That is again very important, and 10% reduction in the cost of energy of that microgrid on annual operation. And cost of energy has increased by 71.6%. Right, because it is a grid connected system, so time of use energy prices changes from 100 to 200%, with selling price to the grid at 100%. 8% reduction in the cost of energy, which has been observed when the selling price to the grid has increased from 100% to 200%, keeping the TOE at 100% level. Right, so operation and performance of PV-based microgrid system has also affected by meteorological operation, solar radiation conditions, temperature, and many other things, right? And geographical equation, grid outage conditions, and so on and so forth. So I think now I have shared you 2 articles, and both articles are very interesting work, right? Do you have any questions on it?
So is there any question from the participant side? Any question?
Because we can cover a lot of things, right? But we know that it needs patience also, and a lot of technical things are there, and that within this lecture we cannot do much more detail, but the key objective is that to motivate the participants to work on a sustainable electrical energy system, and not to work but to utilize this information for educating and training and generations energy policy makers also, so that we can contribute a little bit in achieving net zero ambition of government of India by 2070.
Yeah.
So,
Good afternoon, sir. Yeah. Sorry
Yes,
to
please.
interrupt you. Yeah. Good afternoon, sir. First of all, I congratulate for this insightful lecture. It was really helpful for us. My question is that during optimization, have you considered the stochastic behavior, or you can say intermittent behavior of the PV system?
Yes. In calculating the economic sizing of solar photovoltaic system, we consider the solar radiation data that I have not included here. So it was based on the NASA website for that particular location. So here that data, it was, I believe that it was a 10-minute or 15-minute intervals also. So that real-time variation of the solar photovoltaic temperature that have been considered here. And of course, we have not considered the more stochastic variation of the load profile. Okay, load profile we considered, but that sudden changes or sudden drops that we have not considered. We considered the typical grid outage conditions of 1 hour, 2 hour at random time. Okay, those factors throughout the year at a random time. So those factors we have taken into account. Yeah.
Okay, thank you, sir. One more
Thank
question. Can this data, Gurgaon data you have considered for your research work, from where it is available, or if
Yes.
you
So,
have...
yeah. So this is a very interesting point. And if you refer these two articles, in both articles, the sources of the data are mentioned there. Okay. And by using those sources, you can download the data. And it was a real system at the TERI. And we have the real operational data of the TERI energy system also. So we used that data also. And those data have been published or available, right, through these published articles.
Okay, thank you very much, sir.
So any more questions from the participants? Sir, I have one question, sir.
Yeah, please.
Sir, related to this sustainability, especially to this renewable part, which are integrated with the grid, how we can work on the reliability aspect? Suppose if we talk about a solar photovoltaic, sir.
Yes.
Because as of now, we know that solar panel degrade year by year, and over the 15 years, it is completely demolished. So if we want to do the reliability assessment of solar photovoltaic, how
This
we
is a
can
very, this is a very interesting and very good point. So in this project, we have another component which I have not discussed here. So another component, it was that we know that any technical system has some limited lifetime. So solar photovoltaic systems are also going to have limited lifetime also. If we are not operating that properly, their technical lifetime is going to be reduced. And then we need to do the recycling of solar photovoltaic panels also. So we consider the recycling framework for solar photovoltaic panel. And that project, it was also funded by the Norwegian government also. And that within that recycling frame, we considered that how the technical lifetime of the solar photovoltaic panels are going to be reduced. So that is the reliability question, right? So then we have very good example at the TERI, Gurugram, and at that we have two panels. They were mounted at the same time, not two panels, two arrays, right? Photovoltaic. So one of the arrays, they are having very good ventilation, right? And another PV array, they don't have very good ventilation. So we can clearly observe through our eyes, those who don't have the proper ventilation, how the degradation of them was there clearly by our eyes without using any technical information or the operational data. So this is a very interesting point what you have mentioned. Now we need to work when we are installing the solar photovoltaic system, how the ventilation is going to be there, how the air circulations are going to be there to increase the technical lifetime or the performance of the solar panels. We know that the solar cells or the PV system performance decreases with reference to the operating temperature. If solar cell operating temperature increases, it gets degraded. So to here, now we have to see that, because we are not going to do any forced ventilation, right? We have to utilize the natural ventilation, but how we are mounting them. So that is very important and interesting point. So to have the proper air circulation, and we have the real operational example in this project at the TERI-Gram. If you have some time, if you visit the TERI-Gram, you can see those two set of the photovoltaic arrays, how by through our eyes only, without analyzing the text. So this is a very interesting point. We have to consider the reliability, and that reliability, of course, that depends on the degradation of the solar panels, material characteristic also, and then of course the operational situation also.
Okay. Sir, one more thing is that in order to enhance the efficiency of solar photovoltaic cell, various cooling strategies were opted. So I just want to know
Various what?
cooling strategies.
Cooling. Yeah, please.
So could you please suggest if someone has to work on that in a similar area?
Yes.
So
This is a very
strategy?
yeah. This is a very interesting point, and with reference to our earlier point, like, because let's say if we are putting proper cooling, let's say water cooled system, let's say if it is in very high temperature or tropical conditions and or desert conditions like that. So that is one point. But it's another point, like let's say if you consider our typical Indian conditions, right? So we need to have a proper ventilation and like that. So with reference to your one point, that we can put appropriate integrated water cooling right on the solar photovoltaic panel. And I did one work in cooperation with China long back, I think it's 10 or 15 years before, and that article has been cited many times. So it has been reported very interesting. The results have been reported, experimental results, that how if you do the water cooling of the solar photovoltaic panels, how we can get the lower heat gain also, and how we can improve the performance of the solar panel also. One point. Second point, that is another related to the reliability or the cooling also, maybe more a reliability. So now we know that everywhere in the world we have the dust. Okay, so that dust accumulation, right, is, and depending on the area to area also, is going to impact the performance or the degrade also. So to remove that dust, from the solar photovoltaic system, there are a lot of cleaning mechanisms have been proposed also. So those cleaning mechanisms, now people are thinking to work on electrostatic precipitation or electrostatic principles for removing that dust by charging them and collecting them and improving the performance. So that is also a very interesting point with reference to the reliability or from the cleaning mechanism point of view also. Yeah, please.
Thank you, sir. So, any more questions from the participants? Yeah, anyone? I think so. No questions from the participants, right?
No
So, sir,
problem, but
this is the formal
we
closing
know
of the
that.
session. So on behalf of Department of Electrical Engineering, JC Bose University, YMCA Hyderabad, I, Dr. Abhinav Saxena, in the assistance with Dr. Ravinder Arya, would like to extend our sincere thanks and gratitude for insightful and engaging sessions. Your expertise, clear explanation, and real-world example greatly enrich the learning experience of all the participants. So thank you once again, sir, for the contribution of the success of the program. We will definitely look to the forward, sir. Thank you, sir.
Thank you. Thank you, Abhinay. Thank you again. And please convey my regards to your Vice Chancellor. I met with
Sure,
him in
sure.
April 2025 in one conference of Swadeshi, and we had a very good discussion, and he was inviting
Okay.
me to come to to the university. But always we have some time limitation and other issues
Yeah,
also.
yeah, I can.
Then please convey him that I joined on through online
Yes, sir.
and
So
participated.
can
in
we have a
this.
group photograph, sir?
Yeah, please, please.
Yeah, requesting all the participants, please switch on your camera for the group photographs. Okay, sir. Thank you so much, sir, for accepting our invitation on a very short notice. We will definitely look in the future, sir. Thank you so much, sir. So I request all the participants, please be stay connected. Don't leave the group. Our next speaker, sir, is going to join very soon. Rohit sir, are you there?
Hello.
Rohit sir, are you there?
Yeah. Hi, Abhinav. Am I audible?
Yeah, you're audible, sir. So welcome to the program, sir.
Thank you.
Shall we start?
Yeah, we can start, or if any other participants is joining, then we can wait for 2, 3 more minutes.
Okay, let's wait for next 3 minutes. After that, we will start.
Sure.
Rohit sir, shall we start now?
Yeah, we can start, Abhinav.
Okay, thank you.
Or-
Thank you for your give your consent, sir. So, a very warm welcome to everyone to this session 12 of the AICT sponsored Atal FDP program. So today we have with us a very well-known speaker, Mr. Rohit Saxena, sir, from the Ericsson company here. So, Mr. Rohit Saxena, sir, did his BTech in Electronics and Communication from HMI Institute, IP University in 2011. Sir has a total 14 years of experience in telecommunication field on Ericsson hardware. His major responsibilities are operation and maintenance. His function changes, software upgrades, UPS upgrades, and troubleshootings. Technical problem in BSC, RNC, Node, B, BTS, Aerodep, and Genob. The key areas of specializations are OSS, ENM application, Citrix, application launch, Citrix applications, license manager, software manager, BMS remedy, reflection. So Mr. Rohit Saxena sir is currently working as RAR engineer, GNOC in Ericsson in Private Limited India, and location is Noida right now. So welcome to sir, welcome to this Atal FDP program, and thanks for accepting our invitation, sir. So over to you, sir. Now you can share your screen, sir.
Yeah, sure. Just let me know if my screen is visible.
Yeah, definitely. Now it's visible, sir. Yeah, it's visible now.
Okay, so hello everyone. I can give you a short, brief intro about me. Already Abhinav has explained everything. So total 14 years of experience I have in telecom domain, and currently from past 10 years I have been associated with Ericsson Global India Limited. Before that, I was part of Nokia Siemens, Vodafone, Alcatel, and Reliance Jio, and Huawei, and then back to Ericsson. So currently, it's been 10 years over here, and I have been looking when I started uh, from 2G, and it's continued the journey from 2G to 3G, 4G, 5G, and last till 5G advance. And also, there are testing going on in Australia labs for 6G as well. So I'm associated with that as well, but it's still not a commercial launch. It's just in testing phase. Okay, so let me start with the 5G introduction. So this is the telecom evolution from where we started. From 1G we started in late 1980s, and the technology that was used in 1G, first generation mobile communication, it was the analog technology. So since you all must be aware that analog communication cannot go for longer part, cannot go for long durations. So there was some limitations when we implemented first generation mobile communication. It was only limited to voice only. Firstly, there was no data services, there was no SMS, just the voice calls can be initiated, and a very limited coverage, and also a very limited spectrum for 1G. So that was only limited to voice calling, and also if we want to roam from one place to another, that was also not possible in case of first generation. Then evolution came after first G, when the scientists decided that analog technology is not a good way, it's not a better way for a wireless communication, and they switched from analog to digital technology. So digital electronics and digital technology, we can send signals to very long distances without any physical connections. Just we need transmitters and receivers to send digital signals. So 2G, the evolution started from 1990s, and as per 3GPP, if you have heard about third generation partnership project, this is a company which governs rules and protocols for telecommunication, and all operators or vendors, they need to follow 3GPP guidelines while developing a network, while uh, generating a network, while spreading the spectrum. So they need to follow all the guidelines of 3GPP. So 2Gs, it was a boom like in telecom world, where voice communication was possible for longer distance. We were able to make ISD calls, and also besides that, there was SMS facility, there was data we can serve, we can open the websites, but the speed was very limited. It goes on buffering and buffering. We were not able to watch videos on 2G. So that was the limitation in 2G. And basically in 2G, there was a TDMA frame, the access technology. Access technology is TDMA, time division multiple access, and FDMA, frequency division multiple access. So in 2G, the users were divided on the basis of time slots, and the 2G was limited. The frame structure of TDMA was limited to 4.17 milliseconds only, which has 8 slots. That means one slot will be approx 577 microseconds. So a user in a single frame, there can be maximum up to 8 or 16 users. So 2G was, although it was a good evolved technology for voice communication, but for data surfing as compared to packets, 2G was not that much advanced. We were not able to get higher throughput peak rates in 2G. So then after 2G, the another technology, that is third generation mobile communication, which gave a vast data services. End users were able to watch videos, do surfings. They were able to get higher throughputs in case of 3G technology. So what was actually the logic behind 3G, that we were able to get higher speeds, which we were not able to access from 2G? It was the technology. 2G was using the access technology as time division multiple access or frequency division multiple access. And also the modulation scheme in 2G, it was phase shift keying or BPSK, these two modulation schemes. But in case of 3G, users were divided on the basis of codes. That is, code division multiple access is the technology that is introduced in 3G, due to which we get wider frame structure, wider codes, many users can be accommodated, lot of data can be transmitted. So 3G, because of this technology, CDMA, or I would use a word, since in 3G advanced there was wideband CDMA, WCDMA. So with WCDMA, we were able to accommodate lot of users, lot of physical resource blocks. So users were able to get higher data speed. But that 3G was only limited to end user for domestic purposes. It was not serving the industrial uses. While it comes to big data for clouds, for Kubernetes, then there was a need for more higher data rates. And the scientists decided to change from 3G to fourth generation mobile communication. So in early, I would say 2000, from 2009, the testing was started, and the launch was actually from 2011 December, the industrial launch from 2011 December. So what came into the picture? 4G. 4G was not meant for voice communication. It was not for voice call initially. They thought that already for voice we have 2G, we have 3G. We just need higher throughput. We just need higher data rates. So So voice 4G was introduced only for data traffics. It was not for voice communication. So if you guys have experience, have seen your handset when the 4G was recently introduced, at that time, when you get a voice call on your handset, then 4G changes to either 3G or to 2G. That signal logo on the handset, it changes from 4G to 3G, or from 4G to 2G. So the technology is called as CSFB, circuit switch fallback, because 4G was only designed for packet switch, that packets can be transmitted to get higher data rates, while 3G and 2G had circuit switch technologies as well, since they were serving voice uh, as well. So uh, in 4G, there was circuit switch fallback. Whenever the voice call will come, the 4G will switch to the legacy technology, either to 2G or 3G. Then there was a high demand that operators said, we are buying so much, paying so much for hardware for 2G and for 3G, and then another for 4G as well. So operators demanded that there should be voice in 4G as well, so that they can save the cost. Why to keep the both the technologies? Why to keep all three technologies? Since users just need to provide voice and data. So in later releases from release 9 for in LT is long-term evolution. It is a standard for 4G only. So in release 9 or in release 10, there a feature was developed, that is IMS. IMS, uh, IMS is a multimedia system due to which voice call is possible in 4G, and that voice call is known as VoNR, voice over NR. Sorry, VoLTE, voice over LT. Okay, voice over LT or voice over 4G, you can say. So when IMS was introduced, then voice call was possible on 4G. And when that voice call stabilized on 4G network, then what operators started? They started shutting down 3G, because 3G was no more needed. Already we were getting higher speeds in 4G, and in case if there is some issue in voice on 4G, then a user can fall back from 4G to 2G, or it can hand over from 4G to 2G. So now if you see, very rare any operator in entire world is using 3G. So everywhere it's either 2G or the 4G is deployed. 2G is also somewhat obsolete, but still in some parts of the world 2G is there. And most of the operators has totally shifted to only 4G and 5G. Since voice and data both needs we are getting served from the latest technologies, so we do not require 2G and 3G. And most probably in India we have the operators Vodafone, Airtel, Reliance Jio. These three are the major operators, and they have shut down the 3G services. And soon you will get the news that 2G will also be shut down. Although Reliance Jio there is no 2G, they have only 4G and 5G. But in case of Vodafone and Airtel, they are still having 2G. But what's the reason of still keeping 2G? Because some of the device, some of the users are still on the 2G handsets. If you have seen that machine for debit card machine, it still works on 2G. It do not supports 4G or 5G SIM card. Okay, though it supports Wi-Fi. These days in malls and everywhere, those machines uses Wi-Fi, but in remote areas where there is no Wi-Fi, their machines are using 2G SIM cards. In hilly areas, their machines are using 2G SIM cards. So that's why still operators are using 2G. Airtel and Vodafone still have 2G services. Reliance Jio, you will never see that ATM card machines is using Reliance SIM card, because it do not supports 4G, 5G, and Reliance has no 2G. Okay, So in 4G, we get both the facilities, high throughput and voice quality as well. But still, that high throughput or high data rates are good for the domestic purposes for end users. But when it comes to industrial uses or for industrial purposes, then that speed or that latency was not sufficient. So the technology from 4G shifted to 5G. 5G fifth generation has multiple use cases, and this is going to be the one of the most successful. And even after 5G, when other technologies are going to be launched, then they might be having different use cases, which will be applicable for industrial purposes, but for end user domestic purposes, till 5G, all services, all purposes are served. So what all applications 5G have? 5G use cases are EMBB. This is enhanced mobile broadband communication. MMTC, massive machine type communication. URLLC, this is ultra reliable low latency communication. Even higher speeds, ultra reliable low latency high connection density is possible in 5G. So we have 5G from release 14 onwards as per 3GPP, and the latest release is release 17, which has 5G advanced features. Our study will be focused on 5G only, since 2G, 3G are obsolete technologies almost, and we are going to sustain with 4G, but we will be concentrating only on 5G, on the latest technology only. Okay, so these are the use cases of the 5G. First is enhanced mobile broadband communication. Enhanced mobile broadband communication, simply it is for end user, like it provides voice, web browsing, file sharings, video streamings. So this use case, it was earlier in 4G as well. This was the same use case that is continued from 2G, 3G, 4G, and 5G. Just a better voice quality, good throughput, and higher data rates we are getting in 5G. And what is the technology? Why? How the speed increased? Because 5G uses access technology as OFDMA, orthogonal frequency division multiple access cyclic prefix. So orthogonal frequency division multiple access can accommodate multiple physical resource blocks. A wide spectrum is possible in case of 5G. Another use case is ultra reliable low latency communication. This is a very important use case for 5G. This is the actual use case for what 5G came into picture. This use case is going to serve industrial automation, mission critical applications, augmented reality. Like if I give you example, you must have seen robotic cars. Cars are running on their own. So that is because of this use case, ultra reliable low latency communication. Another application is in case of medical surgeries. Robotic hands are going to do the surgery. Okay, although it's very tough for a patient to get surgery from a robot instead of a doctor, but it's a use case in remote areas where doctors are not available. This use case, actually low latency, what will means ultra low latency? Latency will be very less. It would be lesser than 0.3 milliseconds. Okay, so a doctor is giving a command from some remote location, and that robot is actively acting within milliseconds. So this is the use case. Even in Gujarat, Jamnagar, there's a factory of Reliance Jio. If any of you is aware of, there are no workers. That factory is totally operated by robots. The boxes, they are being put on the vehicles. Those vehicles are auto running vehicles. They are on 5G operators, 5G operated. That vehicles move from one place to another. They carry the goods, they put the goods from one place to another. So that industry, Reliance Industries in Jamnagar in Gujarat, it is using this URLLC use case. Next is massive machine type communication. This is used in smart cities, smart homes, smart buildings, voice, etc. What this means, like you have smart meters, electricity meters, they will remain connected from 5G. The bill will get auto generated from those meters. The bill will auto read everything. Okay. So this is the another use case of 5G. And it do not require a very low latency because bill will be generated once in a month. So it just requires latency of 30 days. That's it. So these are the three of the use cases, and URLLC is the most important use case for which 5G was introduced. This is the 5G architecture. So from here we begin. This is UE, user equipment, that is a handset. In a network, we have two categories. One is radio part, that is called as radio access network, RAN, and one is the core part. Okay, core part is basically actually taking care of call switching, mobility functions, handovers. Earlier at the time of 1G or 2G, when users they want to, or it's good to say 1G or 1.5G, not 2G. When users they want to from landline, when you want to make ISD calls, it was around 90s, somewhat 1990s, somewhat. If user wants to make an ISD call, then operator manually he is sitting at the place and you have to instruct them, I want to initiate a trunk call from such and such place. So he manually uh, pulls out the cable and plugs in to the cable to another server which you want to connect. So that was the part, that was the functionality of the core part, which earlier in 90s manually an operator was doing, but now it has been automatic, and that is being done by this core part. So this is a user equipment, this is a handset, this is a RAN, G Node B, this is a radio access network part. UE is always connected with this G Node B. This G Node B is like a tower which has radios, antennas, which transmits the signals, and UE receives that signal. And UE also, if UE wants to send the signal, it will send the signal, and here G Node B antenna will receive that. Further, G Node B communicates with the core part. So core part has two categories. One is AMF, access and mobility function. Another is UPF, user plane function. So AMF, basically it controls the control plane signaling, and for user plane part, UPF is responsible. So G node B first communicate. So these are all the core nodes: AMF, AUSF, UDM, PCF, SMF, application function, UPF. This part. This data network is then intelligent network. This is another part of the telecommunication where billing servers or user identities or databases are maintained. Okay. If we see access and mobility function, so this is actually the core, I would say this is heart of the core AMF. So it checks the signaling part, whether signaling is successfully set up with the G node B or not. And it also handles UE mobility. If a UE is moving from one place to another, so it will take care of handovers, it will take care of call switching and everything. This AMF is further then connected with authentication center. So authentication center, authentication server function, it provides authentication features. Whenever you make a call, UE is always authenticated. Its information is always registered in a register in a database that is called as UDM, Unified Data Function. Unified Data Function is a database which has all the informations of the UEs of the SIM cards. So whenever you make a call, when you initiate a call, there is an IMSI, International Mobile Subscriber Identity, that is linked to your SIM card, and that IMSI is also registered in this UDM. Then at UDM, Authentication Center checks with UDM whether this is a whitelist or it is a blacklist UE. So authentication is done by Authentication Center using its database information in UDM. Okay. Then once control plane signaling is set up, now you want to initiate the data. Either you want to use the data services or you want to make a voice call. So for that, you need user plane. You need user plane traffic. So for that, GNodeB GNodeB doesn't directly communicates with UPF actually. It communicates through AMF, and AMF creates a session with session management function, and a user plane traffic can be transmitted in that case. So in my 14 years of career, I am only associated with RAN part, radio access network, GNodeB. I have not worked on this core part, and today also we are going to only focus on GNodeB, where we have baseband unit which controls radios, antennas, tower mount amplifiers, and passive elements. Okay, so when 5G was introduced, 5G, there was two ways to implement, to deploy 5G. Either NSA non-standalone, this is a non-standalone, or standalone. Okay, non-standalone, what it means, non-standalone. For non-standalone, I do not require additional hardware. So operators, they do not purchase, in case the operators which are using non-standalone, there is no need to purchase additional hardware. Their cost was saved, and they were able to provide use cases, additional speed, additional throughput, good voice quality with existing 4G hardware in case of non-standalone. So if I let you know about the vendors, we have major three vendors in entire world. One is the Ericsson, another is the Nokia, and the third one is Huawei. So these three vendors are basically producing the products, basebands, radio units, AMFs, core nodes, and operators are purchasing these products from these three vendors. There are other vendors as well, but they are very small vendors. They are serving very small areas, not the complete cities, not the complete countries. So the main leading vendors in the entire world are these three only: Ericsson, Nokia, and Huawei. Okay, so what happens, Eric? Suppose any operator has already purchased 4G hardware. He has the complete 4G network, and he want to provide 5G services to the customer, to the end users. So there is no need to purchase any additional hardware. Okay, so that can be implemented simply in the existing 4G hardware. So this was the non-standalone case, and the word this option is option 3. All we have 7 deployment options for 5G, but only 3 are currently in use in the entire world: option 3, option 2, and option 4. I have not discussed option 4 here because option 4 is also very rare. We are normally using option 3 and option 2 only. If you take example of Airtel, Airtel is using both. Option 3, it has non-standalone 5G as well, and option 2 as well, it has 5G standalone. Vodafone, it doesn't have standalone, it is only using non-standalone. Reliance Jio is not using non-standalone, it is having standalone LT and it is having a standalone NR. So Reliance Jio, it is a big brand. It has a lot of money, so it has purchased separate hardware for 5G. It has deployed separately 5G in another hardware. Okay, so this NSA is called ENDC, E Node B dual connectivity. E Node B. E Node B is the radio access network node. Okay, the node name. In 2G, it was called as BTS, base transceiver station, and in 3G, it is known as Node B. In 4G, it is known as E Node B. E means evolved Node B. And in 5G, it is known as GNB, G Node B. Okay, next generation Node B. So ENDC, E Node B dual connectivity. So here what happens with LT, this 5G side, this G Node B remains connected. This is a LT cell and this is a 5G NR cell. NR means NR is for new radio, 5G new radio cell. So LT and 5G, they remains connected in case of non-standalone. And if you see these dotted green lines, this represents the signaling. The signaling E node B creates a signaling with the core. This is the core node EPC, evolved packet core. As I told you about AMF, the core node, but that is for 5G standalone only. In case of 5G standalone, we have 5GC. This is a 5th generation core, or you can call it AMF, absolute mobility function. But in case of LT, it is EPC, evolved packet core. So we have signaling with E node B, but G node B has only user traffic, only, as I told you, UPF, which is responsible for user plane data. So G node B has only user plane connectivity with core in case of NSA. And for control plane signaling, it has to go from LT, and then LT provides the core connectivity. So G node B is not directly connected with core node in case of NSA, in case of option 3. Okay. So, but there were some limitations in ENDC as well. What are the limitations? Like some features like network slicing. I cannot use network slicing in NSA, but network slicing is supportive in 5G SA. Even the use case of URLLC, ultra reliable low latency communication, it is not possible in case of NSA, because if you are going from G node B to LT and then LT to core, the latency will be increased. First, you need to communicate with latency is what? The time a signal takes to transmit from one place to another. Okay, so firstly, the signaling is to be set up between E node B and G node B, and then E node B sets up the signaling with core. So if G node B needs any information, it has to go through E node B. So actually the latency will be increased. You will not be able to get ultra reliable low latency. So this use case is not valid in case of non-standalone. That use case is only valid in case of standalone communication. Okay, so standalone is option 2. It is a very simple deployment. It has just a G node B, a radio site. Okay, a radio site, radios, and simply they remain connected with 5G core, that is 5th generation, new generation core. Okay, or you can call it AMF, absolute mobility function. And then this is a user equipment which transmits and receives signals from G node B. Any doubts or any queries anyone has? Abhinav, is it going okay?
Yeah, absolutely. It's smooth.
Okay,
It's smooth.
let me continue.
You can go ahead.
Okay, so this is how the 5G deployment took place. So we can deploy 5G in 3 basically spectrums: low band, mid band, and high band. Low band is less than 3.5 gigahertz. Basically from 1 gigahertz to 3.5 gigahertz, it is called as low band, which is also an existing 4G band. So we can deploy 5G with existing 4G band. So earlier, what happened earlier, when there was only spectrum for 4G, then 5G was deployed in existing 4G spectrum. All the operators deployed 5G in existing 4G spectrum because spectrum was not purchased for 5G at that time. Then the mid band is from 3.5 gigahertz to 7 gigahertz. So from 3.5 gigahertz to 7 gigahertz, we have mid band, and that can basically we can use 5G NSA or 5G SA, both can use that band. High band is from 28 gigahertz. This is also the band for millimeter waves. This is a very high band. This is normally used only by 5G SA, 5G standalone, and for the application ultra reliable low latency communication. So wherever URLLC is working, there the high band is used. Okay, in India, only Airtel and Reliance Jio has purchased high band spectrum, but Vodafone is still using the existing 4G spectrum. It has no mid band as well. It is still using the low band. So you can compare while if there are similar coverage from Vodafone and from any other operator, Airtel or Reliance Jio, you will feel that there is data streaming issues in case of Vodafone, but with other operators, it would be going perfectly fine. Okay, 5G standalone is very flexible and it has a scalable design. It is an ultra lean design. It is easy to deploy in the spectrum. Deployment is very easy, has multiple use cases. I already told you about the use cases. Another most important feature in 5G is massive multi-antenna transmission. Here, there is advanced antenna systems were introduced in 5G. So what that feature is, advanced antenna systems, they can transmit multiple signals and multiple signals can be received. Okay, like earlier in till 4G, was only 8x8. 8x8 means 8 polarized signals can be transmitted and 8 polarized signals can be received. But after the after 5G came, we can send from 16x16 to till 256 cross 256 cross signals. That means 256 antenna arrays can transmit and 256 antenna arrays can receive, which can provide a very high capacity for the users. Okay, but when you are using multiple antennas, when you're using 16x16 or 256x256, there is also one drawback. You will be able to provide capacity, but you will not be able to provide coverage. Like if even in the home Wi-Fi's, you must have feel this thing. There are two bands normally earlier operators were providing. That is, one was 4G and another was 5G. So when you use 5G, if you shift to some long distance or to shift to another room, the coverage gets poor. So you need to switch to 4G at that time. But if you are sitting just nearby your Wi-Fi and you switch to 5G, you get a great speed. You get a very high speed, very high throughput, because 5G provides capacity. But in terms of coverage, 5G has very less coverage. It's simply like serial and parallel input transmission. Serial transmission always can be transmitted to long coverage, but parallel can provide capacity, but it cannot give you the coverage. So the use of NSA part was also for that sometimes, because 5G provides the capacity and 4G provides the coverage. So what operators do, they use 4G for coverage and 5G for capacity. And since we have split bearer, so user can simultaneously remain connected with 4G and as well as with 5G. So if you are going longer distance from a G node B, from a radio, from an antenna, then you remain connected with 4G. But at the same time, if you want to use high data rates, you use 5G services. Okay. So this is how they have explained the system plane. This signal uh, specifies the G node B, the radio part, radio access network part. This is the centralized data center. Okay, and here, so here there we have integrated D2D communication with the G node B, like two devices, device to device communication. Two devices are connected with the cell, with the radio, and they are communicating. Even B2B communication from one building to another building, we have in-building solutions as well. So it will come into later picture. We'll let you know. Okay, this is the 5G architecture in terms of radio access network. Okay, so we have four types of RAN deployment. We can use distributed RAN, we can use centralized RAN, we can use elastic RAN or cloud RAN. So RAN, as I told you, RAN has the main part as BBU, base station. RAN is simply a tower which you see from a building, on the streets, or anywhere. Okay, which has multiple antennas mounted on those towers. So it has one baseband unit. Okay, which controls those antennas, those radios. Okay, so this RAN has basically then is called as G node B, which has baseband, radios, antennas. So in case of distributed RAN, this is the case of distributed RAN. This is the deployment, which is the normal deployment which all operators are using. In India, we have 95% of distributed RAN. Okay, distributed RAN is actually this is for commercial use. This is sorry, this is for domestic use as well. Okay, so here we have a baseband, a site. It has radios, and these radios can be multiple radios can remain connected with this G node B, with this baseband. Okay, so that means this is a distributed. Another is centralized RAN. Centralized RAN is it is something like a cost-effective solution. We are using one baseband. We have a single baseband, and which are located in central location, and multiple radios are connected far apart with those baseband units. And radios can be connected from baseband using optical fibers. Those optical fiber links are known as CPRI. CPRI name is like Common Protocol Radio Interface. Okay, so this E means enhance. There is CPRI as well, or enhanced CPRI. Both we can use. For high speeds, we use enhanced, and for normal speed, we use CPRI. So this is the centralized RAN. Another is elastic RAN. Elastic RAN is not a 3GPP specification. This is Ericsson internal solution, which Ericsson has developed. This none other vendor is using on this elastic RAN. It's Ericsson's internal solution. What happens? Two sites or two basebands can remain connected with each other using E5 interface. So this E5 is the interface which is connecting two G node Bs. These are the two G node Bs which are connected, and they are connected by E5 interface. What's the use of this E5? Why this is required? In case of carrier aggregation. What is carrier aggregation? Like if I am connected from one carrier, I'm using one frequency carrier, accessing the data. Okay, what will happen? The speed can be lower in that case. Or suppose that carrier is from low band, so I won't be getting that much speed. Or if carrier is from high band, I will be getting high speed, but I will not be getting the coverage. So if I move far distance from the radios or antennas, the signal strength would be reduced. So if I'm using carrier aggregation, so I have one low band carrier, and that my mid band carrier or a high band carrier will also be superimposed on that carrier. So at the same time, I'm getting coverage, and as well as I'm getting capacity. So this is Ericsson's internal solution. Cloud RAN, the latest upcoming technology, which is it's really started. The deployment is really started in a few of the operators, but not all the operators are using. Cloud RAN actually, Airtel is using cloud. Reliance Jio is going to start. Vodafone is still not using. So Cloud RAN, all radio access nodes are going to come on one server or one cloud platform. What will be the use of that cloud platform? What's the need? Why we need cloud platform? Actually, with the use of cloud, earlier when we have to provide a new, suppose there is any new feature that is going to be introduced in any of the technology in 4G, 5G, 3G, 2G. So I have to develop a software for that. And that software I need to install, I need to upgrade in all the G Node Bs, in all the radios, in all the basebands. It takes a lot of time. It's costs a lot of money to the operators. Okay, but with the help of Cloud RAN, I can simply upgrade. I can simply provide one software solution in a one single server, and all the connected radios or the basebands can use that same software from that server. Okay, so firstly, or a single license can be used, can serve all the basebands, all the radios. Okay, this is all about radio access networks. It is divided into 4 categories. Okay, this is the actual Ericsson hardware. This is the picture of one of the site that is mounted on the rooftop of one of the building. So here you can see this is a baseband unit. Okay, it is a baseband unit, and this is a radio unit. Radio unit has further antennas remain connected with these radio units. These are the cables which are going to radio unit, and radio unit is connected from this baseband using this CPRA cable. Okay, and these are also the other antennas. This is another radio. Okay, so this antenna is looking into this direction. It is serving the users in this direction, and this antenna is serving another direction, basically. So, and here we have one GPS sync as well, which is providing this. It's not visible in the picture. Okay, so GPS sync is also required for this G Node B, so that all the radios, antenna equipments, and the users remain in sync. This is the logical diagram. This is actually representing distributed RAN. So from this baseband, we have multiple radios connected. This first radio, this second radio, and radios are further connected with the antennas. And this is the backhaul connectivity. Backhaul means this baseband is further connected with the routers. Those routers are then connected with the core network, with the AMF. Okay. So here, the backhaul connectivity, there must be routers or switches between baseband and G Node B. Normally, most of the operators are using Cisco routers, Juniper routers. Reliance Jio has their own production. They are using their own routers. And in LTE, in case of 4G, they are using Samsung routers as well. Okay, so these are the baseband units. This is the hardware. This is Ericsson hardware. I don't have pics for other vendors, Nokia, Huawei. I have only for Ericsson. So this is the one of the latest RAN processor or a baseband unit, RAN processor 6651. So these are ports for radios. Radios remain connected from these ports. So you can see that we have around 16 ports and 16 radios can be connected. And further, if I want to extend, then I can extend this baseband and connect another baseband with this, and extended radios can be connected then in that case. 16 to 32, 32 to 64. So multiple radios can be connected from one baseband. This is the sync cable. GPS sync cable is plugged in over here. This is the power supply cable. So power supply unit cable is injected over here, and here is the TN port, that is transmission network port. This TN port is for backhaul connectivity. Sorry, I don't know why this is sliding automatically. So this TN port is basically provides backhaul connectivity. Cable from this TN port, it goes to the router, and then router further connects with the core network. Okay, so this is the picture of from all the views of 6651. This is the front portion, this is the upper part, and this is the backhaul part. Here this unit is the fan unit, because it, since a lot of signaling, it is working on high band and working on mid band, so baseband gets heated, so fan units are required. Or sometimes in areas where there is a lot of traffic, we need to install basebands inside some premises where air conditioners are working to control the temperature. Although it has temperature uh, compensation circuits inside it, but it's still, due to high load, sometimes temperature goes abnormal, so fan unit, a cooling system is required. Okay, AIR 3219. This is the latest radio of Ericsson. Okay, this is the latest radio, and you can see the ports. These from these ports, antennas remain connected further from these radios, and this is one of the sync port. And because radios also require sync, the sync port is in BBU as well, and as well as in radio. Maybe because this is the latest one, so in case of streets or buildings, you can see this type of radios connected on the towers. This is another radio 44. AIR was actually antenna integrated radio. In this, there is no antenna required because antenna is already integrated in it. This is the latest one. There is no, you will not see an external antenna for this AIR unit. This radio has inbuilt antenna in it. Okay. This is the old radio 4432. It is bulky size, and there is no antenna integrated in it, so you need to connect external antennas. You need to connect external rats or external tower mount amplifiers with this, or external passive elements. This is the very late radios of that Ericsson produced, 2219. 2219 means that 2 cross 2. It can only serve 2 TX and 2 RX, 2 transmission and 2 reception paths. And 4432 was 4 cross 4. While AIRs are advanced antenna systems, they can serve up to, as I told you, 256 cross 256. Okay. They are basically they depend on the logical definition, on the logical configuration, on the softwares. But these radios cannot serve. They can only serve 2 cross 2, 2 TX and 2 RX branches. Okay. So for these baseband units or for these radios, we require softwares, we require licenses, we require software solutions. So here you can see this is the example of one of the site of Reliance Jio. So IRJ JDPR NB 0486. This is the name of the G Node B. This is one of the name of the site. Okay, and SWM is the software management, and the upgraded package, which is the current running software package of the node. This is the name of the software. It's 27H20. So these are Ericsson specific softwares. All vendors have their different softwares depending on the different features. So this is the latest software, and this it comprises all advanced 5G features, this software. Let me move to the configuration part. Okay, so if you want to access any G node B, we are able to access those G node B remotely using the servers connectivity. So directly, AMOS is the plugin, AMOS is the command with which we are able to connect to the G node B remotely. So this is the name of one of the site, one of the G node B, and it then connects. This is the connectivity is okay, IP connectivity is okay, and then we have to do LTOL. LTOL means that LTOL, it loads the all the configuration, all the internal modules of the site of the G node B. Then we have command ALT. This is for alarm unit. If there is any discrepancy in the G node B, if there is any glitch, if there is any hardware failures, we can see the alarms remotely, and we can even troubleshoot from here remotely to rectify the hardware failures or software bugs. But sometimes it happens that the BBU or radios get faulty. Then in that case, field intervention is required to replace them. ST field replaceable unit. This will show all the field replaceable units. Field replaceable units are those only: baseband unit, radios, antennas. Those are the field replaceable units. So here you can see that in Reliance Jio we are using two bands, band N28 and band N78. Band N28 is, if any one of you has idea, it is a low band, 700 megahertz. It works on 700 megahertz, while N78, it is a mid band. It works on 3.5 gigahertz. So in for this particular site, for this G node B, it has 6 radios. 3 radios are working on low band, 700 band, and another 3 radios are working on mid band, N78. Further, we have logical unit called cell, STNR cell, show new radio cells. So this is the logical unit. Basically, suppose if a radio, 2 or 3 radios are deployed, and all these 3 radios are looking in different directions. Radio A is looking into east, radio B is looking on west, and radio C is looking somewhere in south or north. So in that case, we need to define a logical entity called cell. So this cell remains connected with the radio unit. So if you see, we have 6 radios and we have 9 cells. What these 9 cells indicate? These 3 cells, 70, 71, 72. They are basically low band cells. They remain connected with these N28 band radios. Okay. Then with mid band, we have 2 carriers. One is 30 megahertz carrier, another is 100 megahertz. This is I'm telling you configuration of one operator specific. Depending on other operators, we can have different configuration. We can have different bands. We can have different frequency spectrum. Okay. So here we can see that we have the cell 63, 64, and 65. So 63, 64, 65, they are from mid band only. Mid band means 78 band, 3.5 gigahertz, and 60, 61, 62, this is also from mid band. But 60, 61, 62 are of one carrier, one type of carrier, and 63, 64, 65 are of another carrier. One is 30 megahertz carrier, another is 100 megahertz carrier. So what is a carrier? Carrier is simply, it is a frequency channel which is used to transmit the information between G node B and a user equipment. Okay, these are the radio channels. We have physical radio channels and as well as logical radio channels as well between UE and the base stations. Okay, and whatever UE wants to communicate with the G node B, so it uses that radio channels to communicate. Then we have this ST carriers with those cells. The carriers are connected. Carriers are same as I told you. we have 2 carriers in mid band and 1 carrier in low band. So the definition will be same, and these carriers remain connected with the cell. Sector equipment function. Sector equipment function is basically a hardware unit. It represents logical entity for hardware. So whatever be the radio, the number of radio units, that much sector equipment function will be defined. So here we have 6. So 6 sector equipment functions will be defined. Okay, so whenever I tell you the basic call flow, how the call originates when UE switches on the mobile phone. So I can not get deep into that, but just can give you a brief intro of that. So whenever UE turns on the handset, what it does, it searches for the BCCH frequency, broadcast frequency. Suppose a handset is nearby any location which has 3 sites, which has 3 base stations, and all three base stations coverage it is receiving. So what will happen? Once it switches on the phone, it will receive the BCCH frequency, broadcast control channel frequency, from all those 3 sites. Now it will check which of the frequency is the best, which is giving the best coverage to me. So UE will determine it by its own, the best signal strength, and it will get tuned to that particular broadcast channel. And then suppose there are 3 sites, site A, site B, site C. It received the coverage of all 3. It received the carrier frequency or a channel frequency from all 3, but it finds that cell A is giving the best quality. So it will latch with the cell A. Then after that, once the UE is registered to the network after switching on, it is connected to the site, or whichever be the nearby site. And now the UE wants to initiate a voice call or a data call. So firstly, what it will do, it has to make the connection with the core network as well. Right now, UE is only connected to radio network. Okay, so there are different protocols which UE uses to transmit the signals to and fro to make connectivity and to initiate the calls. So firstly, once the UE is latched to the network, it will initiate an RRC connection, radio resource connection with the G node B. It will say that I want to initiate a data call or a voice call. Kindly provide me the connectivity end to end. So it will first connects with the G node B from setups the RRC connection. Once RRC connection is set up, then G node B has all the information of the UE, and he knows where UE wants to make the call. Suppose from Delhi he wants to initiate the call to Mumbai. So what G node B will do? G node B will connect with the nearby core node, nearby AMF, whichever is nearest to it, and he will say that the UE wants to initiate the call to the Mumbai. So kindly connect me to the Mumbai core node or a Mumbai server. Then that AMF will connect to the B party AMF, which will be located at Mumbai location. And then once it connects with the Mumbai location AMF, then it instructs that a UE wants to initiate a call. Then that Mumbai AMF will transmit the data to the B party caller that such and such user is trying to access the network. So this is how the call goes through from user equipment to the G node B, from G node B to the core of its own core which is connected with it, and then from core of A party, the one he wants to initiate the call with, the B party, core of B party, and then for core of B party to G node B of B party, and from G node B of B party to UE, the B party UE. So this is how the call is originated and how the call is terminated. Okay. This is a few more configurational changes I have pasted. So here you can see this is the bandwidth. NR sector carrier bandwidth. So BS channel bandwidth downlink and BS channel bandwidth uplink. What is uplink and downlink? Uplink is basically when a UE wants to communicate to the radio or to a G node B, then if it sends the signal, it is called as uplink. And when G node B sends any request to the UE, then that is known as a downlink. Then that is called as a downlink communication. Okay, so here you can see that like 70, 71, 72 were from low band. They are using a bandwidth of 10 megahertz only. 63, 64, 65 are from mid band. They are using 30 megahertz bandwidth. And another 3 carriers from mid band, 60, 61, 62, they are going to use 100 megahertz bandwidth. Maximum the bandwidth, maximum will be the capacity, maximum will be the throughput, and higher peak rates. Okay. So here you can see that we have defined the band list manual. How many bands are configured in a site? Like we have 70, 71, 72 on N28 band, that is low band, 700 megahertz, 63, 64, 65, and 60, 61, 62 on N78 mid band. Okay. CVCU, this is one of the Ericsson specific command to check the software version on which software the node is. So the node is running on software R27H20. Okay, and here the sector equipment function remains further connected with the NR carriers. So they remain reserved by with the NR sector carriers. Okay, let me go back and tell you about the layers. Here you can see we have layer 1, layer 2, and layer 3, L3. These are the 3 basically signaling layers. Layer 1 is a physical layer. Physical layer means the physical connectivity, like a CPRI link, CPRI. Radio is connected with the baseband through CPRI. So the CPRI comes in category of layer 1. Layer 2, these are the logical layer. This is the actual building blocks for initiating a call, for aligning resources to the UE, for taking care of bandwidth, spectrum, everything. So layer 2, we have in layer 2 protocols as MAC layer and RLC layer and PDCP layer. These are the 3 layers of layer 2, which basically once the physical connectivity is set up, layer 1 is set up, then layer 2 connectivity for assigning physical resource blocks, resources to the UE, layer 2 is set up. That is from MAC, RLC, and PDCP. And then in the end comes layer 3 signaling. This is for signaling. Actually, for signaling setup, we have a layer 3. This is like between UE and G node B, there is RRC signaling, radio resource control, RRC. So that comes in category of layer 3 signaling. Okay, we have additional layer 3 in case of 5G SA, which is newly introduced. That layer is with SDAP, Service Application Protocol. So that what's the function of that layer? It connects the QoS flows from radio part to the core part. Earlier in NSA non-standalone, the slicing feature was not possible, but in case of 5G SA, we have slicing, network slicing. What network slicing means? Like I can basically break the resources. I can separate the resources as per the needs. Like if I need resources for gaming, separate resources for gaming. If I need separate resources for enhanced mobile broadband, if I need separate resources for ultra reliable low latency communication, then we can use network slicing feature, and that is only possible in case of 5G standalone. Okay, let's move further. So this is all about 5G basics. Rest 20 minutes are for you guys. If you want have any discussion or you have any questions or queries, you can ask. Abhinav, that's it from my side.
Okay, sir. Thank you. So, is there any questions from the participants? You're most welcome. Because it is most modern topic as of now. There is 5G technology, and very soon this technology will replace Bharat C60 technology. So, if any works would like to work on this area, you are most welcome to ask the question with the speaker, sir. So, questions are most welcome from your end. I think, sir, there is no questions from the participant side.
Okay, thank you all for
Yes.
attending the session. Thank you
Sir,
so much, Abhinav,
yeah,
for
yeah,
giving me the
sir.
platform.
So give me a 2 minutes, sir.
Yeah,
There is a
sure.
formal closing of the every session. So on behalf of Department of Electrical Engineering, JC Bose University, YMCA Faridabad, I, Dr. Abhinav Saxena, in the assistance with Dr. Yoginder Arya, would like to extend our sincere thanks and gratitude for your insightful and engaging sessions. Your expertise, clear explanations, and real-world examples greatly enrich the learning experience of all the participants. Thank you once again, sir, for your contribution for the successful of our program. So can we have a good photograph, sir?
My camera is not
No issue,
working,
no issue.
but still I will try.
You no issue. I just, if it is possible, you can switch on. Otherwise, we can take it in the screen mode right now. So I request all the participants, please switch on a camera for the group photograph. Okay, fine. Now it's done. So thank you so much, sir. Thank you for giving your valuable time.
Thank you all.
Participants, please be stay connected. We have almost 15 minutes time from the next session. So by the time, please be stay connected. I think there could be one possibility that we can, sorry, we can close the meeting now, and we'll switch off. We will again meet after 15 minutes. Okay. So that I'll let you know very shortly. So please be stay connected. Okay. I'm sharing the feedback from of the session on this portal, on this chat box, as well as the WhatsApp group. Kashika? Am I audible, Kashika?
Yes, sir.
It is already in recording mode, na?
Yes, sir.
ठीक है भाई. चलो कोई नहीं, अभी our next speaker is going to join very soon. Okay. Good evening, sir.
Hello, Abhinav. Am I audible?
Yeah, I'm audible to you, sir. You're audible to me, sir.
For some reason, I'm not able to hear your voice.
Can you hear me, sir? Hello.
Can you hear me now? I can't hear your voice. No, Abhinav, it's not coming. Let me drop once and join again.
Sir, am I audible, sir? Hello. Okay. कशिका आवाज नहीं आ रही सर की? हेलो.
सर ने लीव किया था अभी, दोबारा से ज्वाइन किया.
Sir, are you audible? Sir, am I audible to you?
Now you're audible, Abhinav.
Okay. Good evening, sir.
Good evening.
How are you, sir?
Yeah,
So shall we start?
I think it's not coming because of my extended monitor. I have to maybe drop again. Yeah, I think we can start.
Shall we start, sir?
Yes, yeah.
Okay, thank you, sir. So, welcome all the participants and our speaker, sir, on this last session, session 13 of this Atal EICT sponsored Atal FDB program. So today we have with us our speaker, Dr. Suresh Singh, sir, from Energex company. He's working as principal engineer. Okay, so regarding his education, Professor Dr. Suresh Singh, sir, completed his BTech in Electrical Engineering from Institute of Engineering Technology, Bareilly, and MTech from IIT Roorkee, and PhD from IIT Jodhpur. Currently, sir is serving as a principal engineer at Energix India Private Limited. In his current role, he is involved in designing, modeling, and integration studies related to renewable energy projects. Dr. Suresh Singh brings enriched experience over 21 years in the teaching and research. Specific areas of interest are power system, power electronics, control systems, microgrid, and electrical machines. His recent engagements pertain to the design, modeling, and simulation of renewable energy systems. He has a wide experience in the modeling, simulation of renewable energy system using analytical tools such as Siemens, PSSE, PSCAD, PSLF, ASPN, MATLAB, and OpenRT real-time digital simulator. He has completed 100 plus projects, including utility scale feasibility studies, PSSE, PSCAD model development and benchmarking, and integration studies globally, including in the USA and Australia. He has extensive experience working with PGM, ECO, PRIPA, NYSO, and CEA. Before joining Energix, Dr. Suresh Singh served as an associate professor and head Department of Electronics Engineering at JSS Academy of Technical Education, Noida. During his academic career, he has taught several undergraduate level courses in electrical and electronics engineering. Besides, he has supervised several undergraduate BTech projects in the field of power system, control system, and solar and wind energy system. His research focus on mitigation of negative impedance instability in solar photovoltaic DC microgrid is based on the concept of power electronics and non-linear control theory. He developed novel controller to ensure stability and performances. He has published several research papers in the international careers and journals. He is a member of IEEE USA. He is also a member of IEEE technical societies such as Power and Energy, Smart Grid, and Transportation Electrification. So thank you, sir. Thank you for accepting our invitation on very short notice. You're most welcome, sir. So over to you, sir.
Yeah, thanks, Professor Saxena. So I'm glad to have interaction with this group, and I'm thankful to the organizer giving me opportunity to share my thoughts, whatever I have learned over the years from academics as well as industry, right? So let me share my screen, and whenever you have any questions, feel free to stop me.
Yeah, sure, sir.
Yeah. Let me know when you can see my screen.
Yes, visible now, sir. Full screen is visible.
Okay. So today's topic, which I'm taking, is renewable energy integration challenges and path forward. So I think all of the participants mostly are from electrical engineering field, and you see a lot of news around the renewable energy integration around the world. So countries, maybe every country has their plans for going renewable 100%. Some countries even have 100% targets, right? So in that direction, right, when we are thinking making our grids renewable, so it comes with many challenges as well. And those challenges, I'll talk about maybe what could be the challenges, and my focus throughout my presentation will remain on mathematical modeling of renewable energy systems, be it PV, wind, or battery energy storage systems, or any combination of these, which we may call hybrid systems. So let me start here. So this is a brief overview of my presentation. So first I'll talk about some challenges, the major grid events, which has happened in the past, and what was the reason for that we could not prevent those events. And then second, because we are doing a lot of integration these days, so what are the existing IBR performance issues which might be leading to another blackouts or major grid events? Then little bit of history of renewable energy modeling, global trends, right? The growth of renewable energy in general, globally, as well as in particular to India. Then in terms of modeling, where are we stand today, right? Of course, the continuous improvement is going on over the years, and it will happen. Hello.
Sorry for the disruption.
Can we
Yes, sir,
start?
please go. Yeah, sure, sir.
Okay. And then I'll talk about some major things which are kind of shaking the industry at this time. And those things will maybe continue over next decade, right? And then I'll talk about a little bit our company, what we do. And then with that, I'll conclude the presentation. So first, I'll talk about what are we against up to. When we are doing a lot of energy integration, so let's maybe talk about some major grid events. So first is California blackout, which happened in July 2nd, 1996. So what happened at that time? Because of reactor power deficiency in Idaho, the voltage instability was caused in the system, and roughly 2 million people lost access to power, including British Columbia in Canada, Western Mexico, as well as Idaho, Montana, Utah, and New Mexico, California, Arizona. Then second, again, California blackout happened on August 10th, 1996. Western grid experienced another massive blackout. 7 Western US states, 2 Canadian provinces, and Baja California, Mexico. Roughly 7.5 million people lost power, ranging from several minutes to 6 hours. So what actually happened, right? You see this graph on the left corner, right? So this was the profile, yeah, voltage profile measured during the event. So you can see it was a voltage collapse, right? And voltage could not recover for significant time. But when the same event was simulated using the power system simulation models, so this was the behavior which was observed. You see this red plot on the right lower corner. So you don't see any problem. Fault happens and voltage recovers nicely within no time. But the actual voltage recovery was something like this. So that means the power system models were not accurate enough to replicate this kind of fault behavior. Now, so this was the actual system behavior after the fault happens, voltage recovery. And now you see when the models were fixed, right? The appropriate models were used for the loads. So this was the recovery profile. Now you can see that the actual voltage recovery profile as well as the recovery profile simulated from the models, they nicely match. That indicates the requirement of accurate modeling of the power system elements, right? If the power system element could be modeled with this precision, right? So these events could be foreseen and could be prevented, right? If the fault happens and we see that behavior in simulation models, right? Then definitely something can be done in advance, but that could not be simulated. So yeah, this is the difference you see, right? So at the top, you see how the loads were modeled at that time. So you have a simple motor, and most of other loads are considered a static load. But load actually are much more complex, right? You have motor loads, large motor loads, which have a stalling characteristics, right? Then a lot of air conditioner load, which are again have motors, right? And static load, sorry. So that is the importance of mathematical modeling, right? Because if your models are not accurate, so you're not going to get the desired outcome out of those models or any study done using those models. This is again recent event, right? which happened in 2022. Odessa, very famous event, right? 4th June 2022. So this event was initiated by lightning arrested fault on 345 kV level in Odessa area. Fault occurred on 4th at 12:59 p.m. and it triggered a loss of 2,560 megawatt of thermal generation, IBR generation, 1709 megawatt of IBR generation loss from 14 solar facilities, 851 megawatt of thermal, and frequency dropped to 59.7 and recovered to 60 hertz in 1 minute, 20 seconds. So this event was categorized. There's a NERC, North American Electric Reliability Commission. So they usually make standards for reliability and enforce those standards. So they come up with these NERC alerts based on the severity of events, right? They categorize as level 1, 2, 3. So it was categorized as category 3 alert. So this is a pictorial, maybe graph for active power, right? You can see that the active power dropped from somewhere 8,800 megawatt to 6,800 something. And frequency also dropped from 60 to 59.7 hertz, triggering a tripping of various plants. So here is a breakup of what happened, right? The root cause, why the events, why the different plants tripped out of the system. So AC current, AC overcurrent, say 3 facilities, and it caused generation loss of 445 megawatt, voltage phase jump, AC overcurrent, VDC bus, voltage imbalance, slow ramp rate after VRT, momentary cessation, grid over frequency. So I'll maybe talk about what is momentary cessation. And anyone from audience? Are you familiar with this term, momentary cessation? This is particularly for IBR units, inverter-based resources. That could be a PV system or BESS system. Okay, no problem. So momentary cessation is when, based on the terminal voltage, the IBRs go into cessation mode. Cessation means they cease to supply any current, be it active or reactive. So that is called momentary cessation. So these were the event outside India. In US, the major events. So let's talk about what has recently happened in India because of malfunctioning of IBR and the related projects. So in India, from January 2022 to May 23, so total of 31 grid events were observed. And this covers 1,000 to 7,000 megawatt of generation loss, particularly in ISTS connected RE pockets, grid disturbance involving loss of 6 to 7 gigawatt of wind and solar in Rajasthan RE complexes due to non-compliance of LVRT and HVRT events. Badla grid event, again, it happened in the same complex, September 2019. These events pose a significant threat to the grid stability and security. So the major events can be categorized in 4 categories: transmission system faults external to RE plant, transmission system fault within the RE plant, over voltage during line or reactor switching, force oscillations in reactive power and voltage. So this is maybe a bit more detail about one of the event, 15th May 2023. Fault occurred in 765 Badla Bikaner Circuit 1 due to conductor snapping, which caused voltage drop to 0.65. That is maybe clear-cut LVRT threshold, below the LVRT threshold, and then suddenly voltage rose to 1.1 pu, which triggered again HVRT, and it caused a total generation loss of 7,120 megawatt. Frequency dropped by 0.58 hertz, and then cascading tripping of multiple EHV lines on over voltage. The major reason for this event was delayed active power recovery of IBRs. So there is a performance requirement that whenever fault happens in the system, right? Suppose it's a 9-cycle or 6-cycle fault. So active power should recover within 1 second from the fault clearance. So one of the major reasons that, although in simulation, these IBRs might have shown that, okay, active power recovery is not an issue, but in actual practice, the active power did not recover within 1 second. And that was one of the major reasons for this event. Then second reason was LVRT non-compliance. Plant increased Q absorption in a state of injection. So any idea about the LVRT or HVRT requirement? Because I think everyone is from electrical background, low voltage right through, high voltage right through. What is that requirement? Anyone from audience before I go there? Okay, no problem. So low voltage and high voltage right through, basically whenever a grid event happens leading to a low voltage situation or high voltage. So the IBR based or the renewable energy projects are not supposed to trip. They are supposed to ride through that particular disturbance and stay connected with the system. That is one requirement for a given duration. That depends on the voltage, whether the voltage dropped to 0.8 pu or it dropped to 0.5 pu. So based on the voltage level, they are supposed to stay connected with the system for a given time. That is one requirement. Don't trip, stay connected. Second requirement, you need to contribute towards the system voltage regulation. So now suppose a low voltage event happens in the system. So how a renewable energy project can help in voltage regulation? Because if it is a LVRT, low voltage situation, that means there is a deficit of reactive power in the system. Now, to compensate for that, this plant should inject reactive power into the system based in proportion to the voltage drop. So the problem was, the second point you see, non-compliance. So it was LVRT event, plant was supposed to increase the injection of reactive power into the system, but instead it started absorbing reactive power from the system, making the situation still worse. Third point, HVRT, non-compliance. Plant did not trip for voltage above 1.1 pu exceeding 2 seconds. So there's a requirement if the system voltage at the point of interconnection goes beyond 1.1 for more than 2 seconds, plants are supposed to trip out from the system. So that did not happen. So here, clear cut, you can see that the plant did not follow low voltage or high voltage right through requirement as set by the utility company, which is maybe in this case is a central transmission utility CTU or as per the guidelines of CEA. So that was clear cut violation of the grid connection requirements. Similar things happened in America as well. So as I discussed earlier, NERC is a body which continuously makes and enforces the reliability standards, and they also keep on collecting the data from the IBR for different power system, generation owners, transmission owners. So here, based on this NERC report, it was found, this was again related to whether the IBRs are properly following the laid down voltage and frequency right through requirements. So this table shows that because it's a requirement that protection settings of these IBR should be set to the maximum equipment capability. So it was found that high voltage, for example, right through requirement was not set to the maximum in at least 1,399 generators. Same low voltage 209 generators did not follow this. Only 722. Same goes for high frequency and low frequency. So it was implementation of the set standards, set requirements. If NERC mandates that the voltage and frequency right to requirement for these projects would be set to the maximum capability of the equipment, but actually in field that was not happening. And that was causing several grid events and maybe loss of gigawatt scale power from the system and leading to blackouts. So again, you can see here. So here, this solid line, this gives the requirement, right? For low voltage right to requirement and high voltage right to requirement, solid lines. And these dots you see are the settings of individual inverters in different projects, right? So the requirement is that the protection settings of IBRs would be set outside this line, right? No trip zone. So this is the area covered by within this area here. This is no trip zone. So all the protections ideally should be set outside these boundaries. But you see several settings are within this trip zone. So whenever event happens and voltage is around these points, so definitely these units are going to trip, and that sometimes triggers a cascaded failure. These are the voltage right through settings, and this is again same for frequency. So this solid red line gives the requirement for high frequency right through and low frequency right through. So none of the IBRs ideally should have their protection settings within these two lines, right? This area. But you see a lot of IBRs have settings inside the project, inside the no trip zone, as well as several have on the line, right? That means those are susceptible to trip whenever any such frequency event happens in the system. Okay, so that was about some grid events and the problem, why it happens. So there's a clear-cut requirement of strict regulations, right? And at the same time, enforcements of those requirements. So whatever you see in the model, the same should happen in the field as well. So then only you can foresee and maybe prevent a lot of grid events. So this is about modeling. How do we model renewable energy projects, IBRs in general, right? So some of you might be familiar with this, right? So these block diagrams are from PSSE, Siemens PTI, which is one of the, I think, most popular power systems simulation software. Any questions for? Okay, so this is how we model as on today. Even it is much more complex now. We have third generation models. These are the second generation models only. So here we have REGC, which is nothing but a generator model, right? Generator model which injects a set amount of active and reactive current into the network. So that generator is represented by this model, right? I'm not going into detail for the sake of time here. And then you have electrical control model, which is RECB. So here you can see that you have two loops here. One is active current loop and one is reactive current loop. This model is also obsolete these days. So you have much more complex models. But just that how we are modeling these days IBRs, just a sample of that. And then you have REPC, which is nothing but a plant controller. Again, here also you can see there are two loops. The upper loop is for reactive power control. And in reactive power control, so basically the function of power plant controller is to control voltage and frequency, active power, everything at the point of interconnection. So it takes the measurement of voltage, frequency, and it provides to the power plant controller and based on the references and measurement it takes, so it tries to regulate voltage and frequency all the time. So in reactive power control loop, you have different modes depending on requirement from the utility that how the plant should operate. It can be set either to voltage control mode, automatic voltage control mode, or voltage control based on droop. Secondly, it can be set into power factor control mode. Suppose you specify that power factor should be maintained unity at the point of interconnection. So yeah, that reference also can be given. And the last control mode for in terms of reactive power is reactive power command mode. So you directly dictate, okay, this much reactive power I should absorb or supply at the point of interconnection. So that command can directly go. And then the lower portion of this control block that indicates active power control mode. So active power control mode, again, you have a plant reference. So you give what reference, what active power exchange you want at the point of interconnection. And P branch is nothing but measurement. So you have a measurement and you have a reference. So then you have a PI controller, which all the time regulates the active power at the point of interconnection. This lower portion is to provide frequency response. That means whenever frequency in the system changes because of any event, plant is supposed to respond to that frequency. Suppose there is a over frequency event in the system. So in that case, again, the plant is supposed to provide its assistance in frequency control. So if it is a over frequency event, of course, yeah, there is a excess of active power in the system. So that means the plant should reduce its active power injection in the system so as to assist in frequency regulation. Reverse happens when there's a low frequency event in the system. So if there is a low frequency event and plant is not operating at its rated power, of course, in that case, it should increase the active power injection into the system and assist in regulating the frequency. On the right hand bottom corner, so this is how all these models interact with each other. So first you have network, right, which is nothing but your steady state power flow model. Then the first model which is attached to network is generator model, which is nothing but here REGC, and it is responsible of injecting certain amount of active or reactive current. So you have here IQ and IP. IQ is nothing but your reactive current, IP active current. Then the second is, because that has to be controlled, how much active current, how much reactive current it has to inject. So then you have a current limit logic. So this is nothing but part of electrical control system, this portion. And then you have a plant controller, which is on the left here. So this is the level of complexity, maybe even in 2021. Today it is maybe furthermore. So this is how we model a IBR these days. And in addition to these models, you have again protection models, right? Voltage protection models, frequency protection models, which strips the IBR in the event of any voltage or frequency event. And to your surprise, this is how we used to model IBR back in 2008. Nothing but a simple negative load, right? But it has a very intense dynamic characteristics, right? So when you model IBR using a simple negative load, so basically you're not capturing its dynamics. And if you're not modeling, so you cannot simulate the actual behavior, and your system behavior, actual system behavior and the simulated behavior could be entirely different. There won't be any match actually in these two. So these two things to match, that means field behavior and the model behavior. So modeling has to be extremely accurate, then only you can say that my simulated model exhibits the same behavior as the actual plant. And that is the requirement. That's the sole purpose of doing a modeling exercise. Otherwise, what's the fun of doing modeling? Okay, so with that, I'll maybe come to somewhat growth of renewable energy. So this data gives global renewable energy electricity landscape. So I think all of you are aware this is not something new. So renewable energy share in the grid is exponentially increasing around the globe, as well as in maybe individual countries as well, be it India, US, Australia, or you take any other country, right? And here you see major portion comes from solar. So solar is growing very fast. Wind is maybe going in a sustained way. And now, because of the problems faced with the integration of more and more renewable energy into the system, so BESS is also becoming important. So that is also coming up. It's not shown specifically. And then again, small hydro, pumped hydro storage. So that is also coming into the system. And sorry, that particularly helps in preparing the system to host more and more renewable energy projects. This is some data related to India, right? Solar, how the solar is growing. So you can see that back in 2010, it was just maybe 0.16 megawatt, right? Installed, and now it's even 2 years back data, right? 71.8. And we stand at this point, I think, somewhere 150 to 200 gigawatt. For target, as a target, we have 280 gigawatt by 2030, and then 732 by 2050. So you can imagine the scale. It is going exponentially up, right? So if the modeling and simulation is not done accurately, it will be very difficult to manage our grids, right? Because all renewable energy comes with its own challenge. Same goes installed wind power in India, right? So you can see this is also almost going exponential. 140 gigawatt by 2030, that is a projection, and 2050, 323. And something I think on offshore wind also is going to come, and these scales might be further sharp. Battery is also picking up. So by 2030, the target is to bring 34 gigawatt, and 2040, 140, and 2050, 200 gigawatt. So this year is also increasing. So in a way, we are bringing more and more inverter-based resources into the system. And with that, operation of the system is definitely going to get complex and challenging. So now with this scale of renewable energy, it's, I think, impossible to think of a simplified modeling, right? So we need to model renewable energy projects with maybe at most accuracy. So that's the only way forward that we can realize our goals of renewable energy integration, or maybe going 100% renewable. Because you see, you might be hearing every time that, okay, this country is trying to go 100% renewable. Say, for example, Australia is leading that race. Then other Hawaii, island of Hawaii. So there are several small countries, bigger. So they are maybe running behind making their grids 100% renewable. But before we reach there are several challenges to solve. So this is sort of brief summary of global modeling trends at this time. So if we talk about USA, so USA in 2000 to 2008 timeframe, they were doing only steady state modeling, no dynamics. Modeling using wind models, so there was no specific PV models at that time. And if you do fast forward right today, so they are modeling steady state dynamics, as well as different type of modeling platform as well, PSSE, RMS kind of a modeling tool, as well as EMT models using PSCAD and similar softwares. So it has become very extensive, and the integration of projects, a lot of interconnection studies goes into before you can think, okay, you can connect actually to the grid. Australia basically leads this race, right? So as far as the interconnection requirements are there, Australia is the toughest country to connect any renewable energy project into the system. As on today, I think it takes roughly 2 to 3 years in the study phase only before you connect to the system. So you're running in cycles before you satisfy their requirement. Model validation, you need to show that everything is passing their requirement. And 2 to 3 years goes into that. And when you prepare that study report, that runs into thousands of pages. So they have odd 500, I think 450 to 500 different tests. India, so yeah, we started a bit late, but now we have picked up very fast. So if today you compare India, so you'll find that India is somewhere between US and Australia. So our requirements are also very strict now. So we are covering a PSSE modeling, steady state dynamics, PSCAD. Again, we are doing both model validation plant level as well as we are doing power quality studies as well. So it is quite extensive, and the interconnection process is also not that smooth now. So earlier, no study, no modeling, nothing, right? You propose a plant, construct it, and connect it to the grid. But now that is somewhat you cannot imagine of. So same goes for other countries. So every country is picking up, and the interconnection requirements are getting tougher day by day. Because as we say, challenges, so the requirements are becoming strict. You see some grid events, you analyze it, and you find the reason, then you again propose a new interconnection requirement so that that doesn't happen in the future. Okay, with this complex modeling, where are we today, right? So this plot I'm showing, because earlier I talked about that, okay, the sole purpose of modeling is that whatever you see in the modeling, your equipment also shows the same in the field. That means whatever model you prepare, those models actually represent the actual behavior of equipment in the field. So in US, what happens that they don't leave you just by submitting some models before the interconnection. Okay, these are the models we have studied, everything looks fine. Now you let us connect into the system. Very good. Okay, you can connect to the system, but that is not the end of history, right? So they have periodic tests, right? Where you have to conduct a particular test in the field, bring those results, conduct the same test on your model, right? And you benchmark it, whether you are seeing the same thing from the model as well as the actual plant. So here you see they have a requirement of mode 26 test, which is nothing but voltage reference test. So here, this blue you see is a voltage reference. Suppose voltage goes from 1 to 1.05 pu, right? And this dotted curve is the field measurement, data collected from the field. You go in the actual plant, give a voltage reference, or record the reactive power. Sorry, no, this is not reactive power. This is voltage only, all voltage. So dotted is measured voltage, and this orange one, this continuous curve, this is voltage measurement from the simulation. So you see they are pretty close. You see the pretty good alignment between the field behavior and the model behavior. This is again for the same test. So this is reactive power, how it behaves in the actual plant, dotted curve, and how it behaves when you conduct the same test with model. So when you satisfy this requirement, okay, this is mode testing, you do it every block of say 3 years, and then you need to submit the revised models. So the purpose is at any given point of time, the utility should have the most accurate model which exhibits the behavior of actual equipment. So whenever they study their grid models, right, system models for the complete country or the state, right, so they can say with surety that, okay, whatever they are seeing from their models, their actual system is going to behave in the same way. That is the purpose. So every generator owner need to repeat this exercise every 3 years. So frequency is different for different tests. Say mode 26, I think, is 3 years. Then you have the similar test on frequency, right? What happens, what will be the active power response of the system when you change the frequency, right? Say in the field, you cannot change the system frequency. So they give some synthetic frequency to power plant controller, and based on that frequency, active power changes. So here also you see the frequency goes up. This gray curve is frequency going up. And in response to this, you can see the active power starts dropping. And you see the ramp rate, right? And alignment of this measured POI active power. And this blue one is here is data collected from the field. And yellow one is from your simulated model. So you see how nicely they match. So this is the stage we are at. In India as well, this is going to come. So there will be field tests, and you need to ensure that, okay, your model and the actual behavior of the plant matches. Now I'll talk about some things which are maybe kind of shaking the renewable industry or power industry in general. So I'm sure most of you must be familiar with grid following and grid forming inverters. So grid forming inverters is coming up in a big way. And reason is that based on their control, they are more robust. They can provide a very good response in weak grids also. And they don't depend on maybe availability of grid, right? So these are not PLL based. So these are the new things which are coming up in India. We are not seeing yet, but yeah, definitely we'll see soon. So grid forming inverters and deployment you see in isolated grids, islanded grids, for example, Hawaii, Puerto Rico. ERCOT is also applying it to a certain extent. The problem is that when we are integrating more and more renewable energy into the system, so we are losing inertia of conventional machines. And when we lose inertia, so the rate of change of system frequency, that becomes high, right? And because of that, the grid following inverters, which works solely on PLL base, because they track grid voltage and frequency continuously, and based on that, they inject active or reactive current into the system. But whenever PLL is not able to accurately track voltage or frequency of the grid, they are supposed to have a problem following the grid, right? So there is a comparative table, brief one. So as I told, the grid following inverters are mostly PLL based, and they are based on current sources, right? So based on the reference, they inject certain amount of active current or reactive current into the system. They need a strong grid so that the PLL can follow the grid accurately. Fault current contribution from grid following inverters is low, say 1.1 to 1.5 pu, and there's no inertia or limited inertia. If we go to grid forming inverters, so basically there are voltage sources, so they create their own voltage and frequency. You provide the voltage reference, you provide the frequency reference. So these are no more dependent on PLL. So they are best suited for weak grids or low SCR grids. Fault current contribution is higher than the grid following inverters, say 2 to 3. And these are good to provide virtual inertia. That means they kind of emulate the conventional generators. and keep the system stability margins high. Particular application, weak grids, microgrids, high IBR grids. Complexity, of course, is higher, so these are not as simple as grid following inverters. Control is much more complex. So grid forming inverters is a new thing. It will change the power systems around the world. In some countries, they have already made entry, and in some, definitely they'll make entry in time to come. I'm confident that many of participants must be doing a lot of research on grid forming inverters, but that is the news from maybe practical perspective. And this is one standard, IEEE 2800, which was released in 2022. This is also kind of shaking the renewable energy industry. So what is there inside this standard? Basically, it has standards related to reactive power capability, voltage write-through capability, frequency write-through capability, then power quality, current injection priority, phase angle write-through requirements. So in a nutshell, if you say what was there before this standard was released, requirements were much more simple and maybe easy to comply, right? Now with these standard in public, right? So now a lot of maybe almost all utilities around the world have started adopting this standard. That means what happens as a result of that? Interconnection requirements are becoming stricter now. And some of the requirements, OEMs, that means the original equipment manufacturers of solar inverters, BESS inverters, wind turbines, right? They are finding it hard to meet those requirements. And so it is kind of challenging everyone in the renewable energy value chain, be it developer, OEMs, or consultants, utilities. It's making the life of everyone much more hectic now. So this is kind of shaking the world. It hasn't entered into the Indian industry or requirements, but yeah, soon it will enter. Yeah, weak grid condition. Of course, we have maybe touched upon this one, but this is also creating a lot of problem and bringing challenges with the increase of renewable energy integration. You add more renewable energy, so that means you are losing inertia. Losing inertia, that means your fault level in the system will also go down. Short circuit ratio means it is a kind of indication of how strong grid is at this at a given point where you are connecting the project. Low SCR means the fault level of the system at that point is very small, right? So based on the SCR value, we define this SCR as a fault MVA at the point of interconnection divided by how much power you are injecting at that point of interconnection. Suppose your system's fault MVA is 100 MVA, where you are connecting that particular substation, and you are going to inject 50 megawatt of power. So 100 by 50, so your SCR becomes 2. If we categorize the system based on the SCR value, if SCR is greater than 3, so we call that, okay, this is a strong grid. And if it is less than 3, we call, okay, it is a weak grid. If it tends to go down even maybe 1 or less than 1, so we call it very weak grid. Now, what happens with grid following inverters particularly? At low SCR. Low SCR means high Thevenin impedance. High Thevenin impedance, so that becomes challenging for grid following inverters to maintain their stability because of your PLL is not able to follow properly grid. So it becomes very difficult in that case. Low SCR also creates problem in the power quality, because at the same time you are supposed to maintain power quality, say harmonic injection at the point of interconnection, voltage flicker, and say DC injections, all those requirements, it becomes maybe worst when you have low SCR, because low SCR means high impedance. Suppose if you talk about harmonic current limits at point of interconnection, if your SCR is low where the project is connected, right? So with that, the harmonic currents are injected from the project side into the system if they face high impedance. So it is difficult for system to absorb those currents if the CR is high and impedance is low. So those harmonic currents can be easily absorbed by the system. And when these are easily absorbed by the system, so in that case, it doesn't cause voltage voltage emission issue, right? Voltage voltage harmonic issue. So that is the importance of SCR, right? Low SCR, that means it is challenging from stability point of view, it is challenging from power quality point of view. So mitigation, how we address this situation, of course, I talked about grid forming control, grid forming inverters is one option. STATCOM, SVCs, dynamic reactive power compensation devices, plant level coordinated voltage and VAR control. EMT studies, of course, to validate stability in detail. Yeah. Data centers. Yeah, before I go to data center, any questions so far?
Yes, sir.
Yes.
Sir, what is the reasons for low SCR levels?
Yeah, low SCR means you are removing the inertia from the system. You are connecting inverter-based resources. Those are connected with the system. There is no physical connection, right? You are connecting the system, connecting the generator using power electronics. So there's the isolation, power electronics isolation is there. So, and at the same time, you might be displacing some synchronous generator. So overall, inertia of the system is going down. And if you maybe recall, the fault current capability of synchronous generator is way above the power electronics, right? They can supply your fault currents maybe 6 to 7 per unit of its rated current.
Yes, sir.
But when you go to inverter-based resources, so they don't have that capability. Hardly you can go to maybe 1, 1.25, 1.3 PU. So that is what creates a low SCR situation.
Okay, sir. Thank you.
Okay. So next big thing which is coming to this power industry are data centers. So everyone now is familiar with AI tools, right? Most of people are using now. But at the back end, right? So all that data processing, data is dumped to data centers, right? And now the data center size and number of data centers is growing rapidly. So you'll find maybe data centers 400 megawatt, 500 megawatt, 1 gigawatt data center single, and then at the same time number is also growing very fast, AI and all those things. So from grid operation and stability point of view, these data centers are a big challenge based on their load behavior, and the size is also big, right? So suppose there are 100 data centers. So the total capacity of these data centers could be in multiple or thousands of gigawatt, right? Or maybe hundreds of gigawatt. Now, what happens when you're writing some query to AI, right? So your server might be running at 100% capacity. Next time, no query is coming, right? So it is at 0 power. So that means the behavior of data center loads is very different, right? At times it can shoot up to 100%. At times it can go 0, right? Now you imagine, right? You are maintaining a grid stability, and then suddenly 100 gigawatt load goes away from the system. So it is very difficult to sustain such a big load going from the system. Same time, you are seeing 0. Next second, you might see that 100 megawatt load is connected into the system. So that is a magnitude of change, right? Grid has to handle. So that is also a big challenge. Secondly, the overall behavior, because these loads are composite loads. So you have motor load, you have air conditioning load, and then you have UPS load, right? So that also is having a very complex dynamic characteristics. So a lot of research is going on, because if you talk today, nobody completely understands the data center load behavior. So a lot of work is going on, how to model accurately data center load, how to study, right, and what requirements should be placed around the connection of data center, right, the interconnection requirement. So a lot of work is going on. Definitely these are going to change the way power grids are operated. Okay, so content-wise, I think I'm okay. I have covered all the slides. Maybe before I go there, because after that there's a slide, a small introduction about the company I'm working with, and that's it. Yeah. So if you have any questions so far, we can take the questions first, and then maybe I can cover the last few slides.
I think so. Please go ahead.
Okay.
There is no
Yeah, I
question for
can
the
understand. My session is last. People are.
No. You can extend up to 6:30, sir. You have 30 minutes time, sir.
No problem, but still I can understand the feeling, right? It's already late.
No issue, sir. Take your time, sir.
Okay. So actually I come from Energins, and we are specialized in renewable energy modeling and interconnection studies, right? So this company was set up in US back in 2013 timeframe. And we started operation in India in 2018. So at present, we are having 3 offices in India: Hyderabad, Bangalore, and Gurugram. 1 office in Australia, 1 in Canada, and of course, US. And in times to come, we are going to enter Europe as well as Middle East. So what we do basically, so we work with developers. So that is one type of client we work with. So developer, what we do, because when they file application for interconnecting any renewable energy project in any country, right? So they need to submit the models of their project. Those models could be in different softwares depending on the requirement in a particular country. Somewhere it could be PSCAD, somewhere it could be PSL, PSSC, and maybe any other software as well. And a model validation report also. So that is one job we do. We prepare the plant level models, validate against the set utility requirement, and submit the package. Then post submission support also. I showed you that mode testing results, right? Post commissioning, field test, and validation. That is, we also do that from the design stage, right? Starting when the developer thinks about, okay, where should I build a plant and what should be the megawatt, right? So finding that location, that comes under feasibility. So we do electrical feasibility. So one is maybe solar resource, wind resource, not that kind of. Whether suppose you choose a substation in Delhi somewhere, and you think of, okay, I'm going to build 100 megawatt solar around this location and connect at this particular substation, maybe 130 kV. Now, that substation, whether you can actually inject 100 megawatt at that point, so that has to be confirmed first before you plan and execute that project. So capability wise, it could be from 2 different perspectives, right? Whether that substation has physical equipment to facilitate the connectivity of your project. Second, whether you can actually inject without causing any overload in the system, nearby system. So that need to be find out, okay, what is the maximum size I can build? without overloading the system. Because when you overload the system in India, usually utility makes systems for you. Suppose you are overloading a transformer, you are overloading a transmission line. So most likely, if it is not your dedicated transmission line, government is going to fund it, right? They'll build it for you and you can inject your maybe power into the system. But in other countries, this is not the situation. If you are cause of any overload in the system, then you have to pay for it, upgrade. Suppose a transmission line need to be upgraded and it needs maybe 1,000 crore, right? So then you need to share that cost. Suppose there are say 100 generators, 100 developers project which are overloading that line, then they need to share the cost for that upgrade based on their contribution towards that overload. So they have a cost allocation strategy, but yeah, in India that is not there. Usually government built the system. So that is feasibility study. We start from that point. We can prepare the design, single line diagrams, interconnection package, everything. So that is one dimension of our work. Second is equipment model development, because when you develop plant level model, suppose you are building a solar project, 100 megawatt, right? And you are using, say, ABB inverters, and you are using, for example, ABB, I'm just making a power plant controller, right? So now to make the plant level model, you need model of that solar inverter, ABB inverter, and you need a model of ABB power plant controller also. In the same software, suppose you are building a model in PSCAD, then you need a PSCAD model of inverter, you need PSCAD model of PPC also, that power plant controller. So that job also we do. We develop models of equipment, inverters, wind turbines, power plant controllers in different softwares. So that dimension goes towards OEMs, equipment manufacturers. So that is the second vertical of our work we do. And the third is we also work for utilities, right? Because when you do planning studies, 5-year plan, 10-year plan, right? So you do a lot of studies using the system models. Say in India, suppose we are doing some 5-year plan, right? So you'll be doing several simulations to see how the, say, 2030 scenario will look like, how much generation will increase, how the load will look like, how the system will behave with that load and generation. That is one dimension. So we also do that part. And other dimension of utility side studies is that, okay, you have submitted your plant model, that, okay, my is behaving well when I'm studying individually. When it goes to utility, so they will connect it with the complete system and then study it. So that is usually called system impact studies for utility side. So that also we do. And we also do the compliance support. Suppose in US, you have NERC compliances, several compliances related to different reliability requirements. So we also provide that support. So this is a kind of business we do. Our kind of business we do comes from US. So we cover almost entire US, Australia, India, and little bit of Middle East. So far, I think we have completed roughly more than 150 gigawatt of renewable energy projects. In number, that could be, I think, in around 1,500 projects or some more. So this is kind of a USP, deep industry expertise in engineering analysis, extensive experience working with all ISOs or utilities in US, Australia, India, Middle East. Experience with all stakeholders in renewable energy development, be it developers, financial organizations, utilities, equipment manufacturers, geographical diversity. So you can see that we work in almost all time zones, cover experience across several platforms. So this I already talked about. So we start with origination when you think about, okay, how much to build and where to build, right? And then preparing the interconnection package, equipment modeling, and energy power economics studies also, that goes into a framework of a time frame of 20 to 30 years. These are the softwares. I hope all of you will be familiar with these softwares. MATLAB, at least I'm sure everyone uses MATLAB. Then SPEN is for short circuit modeling. So I think many softwares are utility or industry oriented softwares. Academics, I think they are not used that much. So SPEN is particularly for short circuit studies, plant predict, again doing the energy studies for say energy prediction studies. PSCAD, again EMT kind of simulation, so you can do all EMT kind of simulation. AutoCAD again is for drawing. AB ProMod is for economic studies. PSLF, again, you can do steady state or dynamic studies. This is very much similar to PSSE, then Siemens PSSE. PVSYST, again, energy prediction and modeling studies. TARA, again, contingency analysis, deliverability. So this is mostly used by utilities, California ISO, MISO, and PJM. I think they use it extensively. Then you have software DSA tools where you have TSAT, SSAT, and all those tools. Big Silent Power Factory, which is popular in Europe, Australia. ETAP, which is used normally for engineering studies, say harmonics, relay coordination, insulation coordination, and all those things. EMTPRV, again, similar to PSCAD. And NVision is particularly for GIS mapping of substations, right? So in US, we have done mapping of almost all substations, right? So we can show you all the substation, be it 345 kV, 230 kV, or 138 kV. So we can show you all the substations on a map, and not only their location, with maximum capacity available, right? What is the available capacity at that particular substation? How much can be connected? And that can be refreshed whenever you run your power flow simulation, so you can get the latest data, right? Because what happens every year, some generations are coming into the system, some are retiring, and then in terms of load also, new loads are coming, new infrastructure is being built. So with all that, so that means your power system is changing every time. So you would know that, okay, last year I could maybe connect at this particular substation, say available capacity was 500 megawatt. Now I could not make my project in last 1 year. So next year, say if I come in 26, right, what will be the available capacities? All those kind of studies we do. And NVision is particularly for GIS mapping of substations. So these are the softwares. You see almost all softwares which are being used in this space. We have each one with us. This is a kind of client base we have. So this slide is a small, we could not cover all the clients we have. So here you'll see representation from all. So equipment side. So I'll tell you a few examples. TMAC, which is nothing but Toshiba. Then you see Tesla. Tesla is kind of Mercedes-Benz in inverters. You see then SMA falls in same category. So in terms of developers, you see maybe you are familiar with Adani, Tata in India, and maybe similar project, similar clients in US, Desiree. So you'll find representation from all three categories: utility, equipment manufacturers, and developers. So yeah, this is my last slide. So overall, we see, and it is going to happen, that interconnection requirements and the regulation would increase with repenetration. The more and more we integrate, the requirements will get stricter. It would get progressively harder to interconnect the projects. And that is happening because earlier, if you see, there was no waiting time in India, right? You construct and connect. Now that timeline is at least a year or 2 years. So you make a design, then you prepare a confo package, submit it, they'll review it, they'll find several flaws, then it will go into several updates, and then finally you'll get confo package. So it is becoming incredibly difficult to interconnect the projects. Now, to solve this problem partially, what should happen that your design and engineering should go hand in hand, right? So whether you design it optimized, whether it can lead into any problem later on, right? Equipment selection. Suppose you go with equipment manufacturer A, will that lead you some problems because of they are not that reliable? So that kind of a study maybe requirements that it should go hand in hand, right? One side you're thinking your design is going on, other side you should also get moving all the studies. A sound engineering analysis definitely will de-risk the project. You have a accurate modeling of equipment and then plant. If so, definitely the strike rate would be definitely higher if your designs and models are accurate. Engineering automation reduces the cost because I told you that in Australia, you need to produce a report of say 1,000 pages, 500 odd tests, right? So that is difficult to do manual, right? And then again, suppose you benchmark the performance, say maybe between two softwares, say PSSE and PSCAD, or between field or one of the simulation software. So if you do it for say 1,000-page report, so yeah, that will run into years, right? So automation definitely is a need here that makes such a difficult task easy and you can handle. Otherwise, it's very difficult. Manually, it's kind of impossible. Mathematical modeling allows you to overcome challenges down the line, right? If you model accurately, you study accurately, definitely you'll see less problems in the field, right? You can foresee the problems. Trust but verify what you receive, right? So that validation is also very critical. Mathematics and modeling are your friends, definitely, because batteries, GFM inverters, hybrid projects, data centers, and I did not touch on this one, electrolyzers, right, are the future. So with this, I'll end my presentation. Thank you everyone for your kind attention. I'll be happy to answer if you have any questions.
So normally in the inverter which you have taken here, what level you are considering for this renewable energy integration?
Level means?
Like level 2, 3, multi-level inverter operation. Huh? I'm asking for that.
Okay, so yeah, multi-level, I think is not that much in practice yet, but yeah, that model usually comes from OEM only, right? And in terms of levels, so you don't have that much levels which you see in research. And because in research, you see in control-wise also, you see so many AI-based controllers, right? This controller, that controller. But actually in the field, the control is still ruled by simple PI controllers.
Yes, sir. It was okay, and thank you, sir. So, sir, one more minute, sir. So, any questions from the participants? Any more questions from the participants? Please let us know. Okay, I think, sir, no questions. So, just a formal closing of all these sessions here. So, it is just on behalf of Department of Electrical Engineering, JC Bose University, YMC, Faridabad, I, Dr. Abhinav Saxena, in the assistance with Dr. Yogendra Arya, would like to extend our sincere thanks and gratitude for insightful and engaging sessions. Your expertise, real-world applications are really greatly enriched the learning experience of all the participants. So thank you so much, sir, for giving your contribution for the successful of our program, sir. Thank you so much, sir.
Most welcome.
Sir, can we have a group photograph, sir?
Sure.
So participants, please switch on your camera. Okay, fine. Okay, sir. Thank you so much. Thank you so
Okay.
much, sir.
Thanks, everyone. Yeah. Have a good rest of the day.
So participants, please be stay connected. In the next 10 minutes, we are about to start the valedictory ceremony of this FDP program. After that, we will conduct a online quiz. So we will have a valedictory program from 6:30 to 7, and from 7 to 8 we have a this online quiz. So please be stay connected. अरे रुक जाओ यार. Kashika, are you there?
Yes, sir.
I think we should begin the valedictory ceremony of this FDP.
Okay, sir.
Okay. So I think it is already in the recording mode now.
Yes, sir.
ठीक है, start करो फिर आप.
Good evening, everyone. Myself Kashika from JC Bose University of Science and Technology, YMCA. I would like to thank everyone for joining and to the experts for delivering the session and making Atal FDP 2025 to 26 a successful event. Now, I would like to invite Program Coordinator Dr. Abhinav Saxena sir to deliver the vote of thanks.
Kashika, I think is basically a briefing of the program. Vote of thanks will be delivered by our honorable chairperson, sir. So a very good evening to one and all present here. So this is Dr. Abhinav Saxena here, coordinator of the program. So very smoothly the program has been conducted in the assistance of the Dr. Yugandhar Arya, sir, the coordinator of the program. Before I start the briefing and summarizing about the total sessions of the FDP, I'll give my sincere thanks to our honorable Vice Chancellor, sir, Professor Rajiv Kumar, sir, honorable Registrar, Professor Ajay Ranga, sir, Dean FET, Professor Rajkumar, sir, Chairperson, Department of Electrical Engineering, Professor P.R. Sharma, sir, and all the teaching and non-teaching staff of JC Bose University of Science and Technology, YMCA, Faridabad, for their continuous support and motivation for the FDP. I also give my sincere thanks to AICT for giving us the opportunity to conduct the FDP in the online mode. The 6 days AICT sponsored Atal Faculty Development Program has been conducted from 17th November to 22nd November 2025 to the online mode on the topic Advanced Trends for the Optimization, Protection and Control in the Electrical Based Systems, organized by the Department of Electrical Engineering, JC Bose University, YMCA, Faridabad. So there were total 13 sessions of the program, which were given by our eminent speakers. So if we start the journey of this FDP, the beautiful journey of this AICT Atal Online FDP begins on 17th November 2025. So on that day, we were having 2 sessions. So in the session 1, we were having a very eminent speaker, Dr. Sanjay Yadav, sir, from CSIR NPL Delhi. He delivered a talk on the topic Role of Meteorology for the Nation Building with a special reference to Visit Bharat 2047. Further, our next session 2 was delivered by the speaker, Dr. Soham Datta from the Open Access University, from the Open Access Technology India Private Limited, and he emphasized about the island detection approach in the microgrid using machine learning. So in the day 2, that is 18th November, there were 2 sessions. So in the session 3, we were having a speaker, Professor Mukhtar Singh, sir, from DTU New Delhi, and sir has really put a focus on the grid stability issue by reducing the inertia due to the increasing penetration level of RES and their remedies with the support of various topologies and optimization techniques here. With the proceed, on the same day, the session 4 begins with our eminent speaker, Mr. Anuj Kumar. He is the manager in the Grid Control of India, and he emphasized on the various operation plannings, challenges, on the current Indian grid scenario. So he told about the various frequency operation control, voltage operation control, how this India is working on it, how it can be further compared with the other countries' operation technology, and what methods can be opted for the improvisation of frequency and voltages on. Further, on the day 3, that is 19th of November, the session 5 begins with the speaker, Dr. Shivani Sharma, Principal Technical Consultant, Hitachi Energy Limited. Ma'am has focused on the large renewable energy and distributed energy sources, DER. After that, she focused on the protection and control perspective of the various hybrid power system, including the renewable and unlimited system here. So ma'am has also shown the clear perspective about the real-time application and the various simulation model of this grid integrated power system network. Further, on the same day, we have the session 6 with our speaker, Dr. Ranesh Kumar Singh sir, Associate Professor from Jamia Millia Islamia, New Delhi. Sir has given emphasis on a very emerging topic, that was the neurocontroller, which was a simply innovative approach in which the dynamic pole motion control has been estimated. And such neurocontroller, we have observed that during the whole lecture, that neurocontroller technique can be implemented in any electrical system, like in any, whether it is related to power system, power tonics, something, any grid connected network. On the day 4, that is session 7, begin with our eminent speaker, Ashish Srivastav sir, from the Skill Vishwakarma, from Sri Vishwakarma Skill University, Palwar, Haryana. Sir has really focused on the electric vehicle. Sir has focused on about the electric vehicle and its current trends, challenges, and the opportunities. After that, Sir has also discussed the operation control of the electric vehicle system with the support of various DC-DC converters. How, if we can propose, we can use the various topologies and the various configuration of DC-DC converter. In that case, we can have a better control on the electric vehicle. Further, on the same day, the session 8 begins with our speaker, Dr. Nishant Kumar from the IIT Jodhpur. Sir has focused on the meta-heuristic optimization technique for solar-powered electric vehicle. So it was simply like an integration of the renewable energy system with the electric vehicle system using the support of this DC-DC converter. And Sir has also shown the various comparative analysis with the various topologies in the real-time system as well as the modeling-based system. Further, on the day 5, that is 21st November, the session 9 begins with our eminent speaker, Professor KPS Rana sir from NSUT New Delhi. Sir has really embarked a knowledge on maximum power point tracking of the solar photovoltaic cell with the various topologies like part-time and observe, incremental conductance, and various AI techniques, and under the partial shading methods. So this was really an interesting session, and we really get a lot about it. This topic really helped the young researchers who are working on the electrical based systems. On the same day, the speaker 10, so session 10 begins with the speaker, Professor Ramesh Bansal sir from the University of Sharjah. So Sir has delivered the talk on the renewable energy integration in the smart grid environment here. And on the last day, that is today, 22nd November, we have 3 sessions. So today, the first session that is session 11, begin with our speaker, Professor ML Kole sir from the University of Agder, Norway. So Sir has delivered a talk on the operation of distributed energy system as the active generator for the reliable microgrid functionality with increasing solar photovoltaic penetration under the PM Surya Ghar initiative. So this was the whole scheme as opted, and this whole setup was established in a Gurgaon-based company. So this was really interesting topic. As of now, Sir is working in University of Agder, Norway right now. So he has also extended his work with some new advanced technique here. Further, the next session, that is session 12, begins with our speaker, Mr. Rohit Saxena from the Ericsson Private India Limited, Noida. Sir has focused on the 5G radio network and its advancement and its applications. So Sir has begins the journey of various radio network by using 1G, 2G, 3G, 4G, further 5G. He has also emphasized on the technique how the 6G can be, how it will come into the market and how it can be beneficial over the 5G technology. So under the various sensors, various chip, and various microcontroller techniques, it was that we have studied. On the last session, on the last day of this FDP, that is a session 13, was delivered by our eminent speaker, Dr. Suresh Singh sir from Energix company. So Sir has really embarked on the topic renewable energy integrations with the various challenges and path forward. So if I conclude all these sessions, so one thing it is observed that our eminent speakers has emphasized the various challenges, various operation control of electrical bus system. And our electrical bus system includes like the grid integrated system, especially the EV, and the integration of electric vehicle systems and this various grid with the renewable energy system, and how this renewable energy system can support both EV and various this grid integrated system under the different challenges. Suppose it was observed that like a different synchronization. If we have to maintain a synchronization between the renewable energy systems and the grid, so we have to opt various topologies. So with the help of the real-time systems and the modeling and simulation, we have learned about this challenges and this operation and control. And various authors, various speakers has also emphasized on the electric vehicle system. And in that we have learned about the battery charging, discharging, and the major concern is the battery costs that we have seen. And the next part, if we see like the regenerative braking actions of an electric vehicle here. So as we have seen, a lot of topics has been covered up in the FDP. So it means there we have a lot of opportunity. We have a lot of opportunity for working on this topic to extend their research. So this will really help the young BTech students, young MTech students, especially the PhD scholars, those who are working and those who have taken that's all. But those who are planning to pursue PhD, these are current topics in the electrical engineering, which will really help them to excel their research. So once again, on the Department of Electrical Engineering, I really extend my welcome and thanks to everyone. But not last but the least, at the end, this FDP cannot be completed without the active participations of all the participants. Because there is no doubt that all the participants were continuously active and they spare their valuable time beyond their working hours and their personal commitment. So I'm highly thankful to all the participants for making this FDP successful. Your participation reflects a strong commitment to a continuous learning, academic excellence, and professional growth. We look forward to your enthusiastic involvement in the future programs and hope this program contributes meaningfully to your academic and research journey. Thank you so much. Thank you, and a great journey here. Thank you so much. Thank you, everyone.
Thank you, sir. Now I request Program Co-Coordinator Dr. Yogendra Arya sir for the same.
Thanks, sir. Dr. Abhinav Saxena have summarized the various lectures conducted in this Atal FDP. First of all, I thanks our Vice Chancellor, Professor Rajiv Kumar, who give permission to conduct this FDP. Then I also thanks our Registrar, Professor Ajaranga, and Dean of ET, Professor Rajkumar, and our Chairperson, Professor P.R. Sharma, who have helped us and motivate us to apply this FDP. And I also thanks AICT to accept our proposal for this FDP. So this FDP conducted in 13 various sessions, 13 out of which 7 sessions were academical and 6 sessions were delivered by eminent industry persons. And in academics, we have also requested from abroad to deliver the lectures. So our request, on our request, Professor M.L. Kolle from Norway and Professor R.C. Bansal have delivered their lectures, and they discuss about the various renewable sources integration in the existing grid, and what are maybe the implications of renewable energy sources on the existing grids, and what are the challenges. Other eminent speakers from the academia relates to the various eminent institutions like DTU and NITs, IIT, and NSUT. So I think all participants have been highly benefited from this FDP, and research scholars will also be benefited to pursue their research further. And finally, I thanks all the participants who participants were around 120 participants. So they were sincere during this various sessions. So I also thanks these participants, and hope we will conduct this type of FDP in near future. Thank you. Over to you, Abhinav sir. Abhinav sir.
Thank you, sir. Thank you so much. Now the podium is on.
Thank you, sir.
Yeah.
Yes, sir. Now I request all of you to kindly share your feedbacks or input for the session.
Feedback from your side, because we are continuously speaking from the last 1 week. Now it is your turn to give us your valuable feedback if any suggestions required for some improvisation in this FDP. You're most welcome.
You are
Please-
most welcome to give your feedback. All participants are requested to give feedback.
Yeah, please give a valuable feedback. Anyone of you, please.
Good evening, sir. Sandeep Rangit this side.
Yeah, good evening, sir.
Overall experience was great and learned lots of new things from eminent experts' experience. And I hope in next time the department should arrange it in offline mode, so we can more interactive, and we can learn some more in more interactive way, and include some simulation part also, hands-on on.
Yeah, sure.
Thank you very
Thanks,
much.
Sandeep. Thanks, Sandeep. We will try to conduct this Atal FDP in offline mode. I think you know that we also had conducted Atal FDP in 2024 in offline mode. So
Yes, sir. Yes.
in future, we will also do the same thing.
Actually, in offline mode, interaction level suddenly increase a lot.
Yeah. Actually, during the offline mode in the March 2025, that is what I'm talking about, we were also having hands-on session. We have provided them simulation workshop, and we also showed our electric vehicle laboratories hands-on session. So definitely, participants will gain a lot from it. So next time, definitely, we will consider this request, and we'll try to conduct offline FDP with all the considering sessions.
Thank you, Dr. Saxena, and thank you, Arya sir, for organizing such a nice FDP.
Thanks,
Thank you
Sandeep.
so much. Thanks, Sandeep. So
Anyone? Other
please give your
participants?
valuable suggestions. Any participants, please give your suggestions. Any feedback?
Yeah, good evening, sir. This is Professor Nishit. I am from Tirthankar Mahavir University, Moradabad.
Yeah, very good evening, sir.
I had word with you earlier as well.
Yeah.
Sir, these sessions were nicely organized, and one thing which liked about conducting session is all sessions were on time. So thank you very much for this. Though I'm driving, so I'm not having much liberty to speak more. But
Thank you, sir.
yeah,
Thank you, sir.
but overall it is a good. Overall, it was a good FDP, and all sessions were nice, and all resource person were to that level. Actually, this was the useful one to all participants. Thank you very much, sir. Huh?
Thank you so much, sir. Thank you for giving your valuable suggestions, sir.
Ji, sir.
Yeah, thank you, sir. So I need more feedbacks and the inputs from the participant side. If it is possible, please give your feedback.
Hello, everyone. Myself, Dr. Shakuntala. Yes.
Yeah, good evening, ma'am. A very good evening.
Very good evening, sir. I found this FDP content, especially, very enriching.
Thank you so much,
And
ma'am.
all the sessions were very informative, practical, and research oriented. Practical means industry oriented.
Okay.
And the experts explained the advanced concept with real-time example and case studies. Moreover, the interactive sessions were interactive, no doubt. That helps in collaborative learning. And overall, I found this FDP very well coordinated, and it will prove beneficial for the researchers, for the faculty members, and the students. Yes, offline, if in future try to conduct in offline mode,
Sure,
just to
ma'am.
have hands-on experience.
Yeah. Definitely. We will consider and incorporate all the suggestions, ma'am.
Thanks,
Thank you so
madam,
much, ma'am. Thank
for
you
your
for
valuable
giving your valuable suggestions.
feedback.
Thank you, sir.
Good
Yeah,
evening,
please,
sir.
ma'am.
I hope
Yeah, good evening, ma'am.
this is Dr. Preeti, sir.
Yeah.
Actually, I want to share the feedback for the FDP, and
Yeah.
the complete FDP was very highly informative, sir. Completely varying from the theoretical sessions, the industrial based sessions also, and it was well structured also. So basically, it was a complete blend of the theoretical knowledge and the practical exposures. Actually, that is in the field, varying from the renewable energy systems, electric vehicles, varying from the power electronic converters also. And discussions on the recent advancement also was very valuable as well. So overall, the experience was very knowledgeable and insightful, and I had a very learning experience from the FDP side.
Thanks a
So
lot,
thank you
madam.
very much. And it
Thank you,
was
ma'am. Thank
thanks
you.
to both of you, sir, for well coordination and all the timely sessions. So thank you very much, sir.
And this FDP will not be possible without the support of all the participants.
Yes, of course, but of course you take the initiative, sir, for conducting and thoughtful sessions, gathering all those experts from the national, international experts and the industries. Of course, that is also very much difficult at the part of coordinators.
Yeah.
So we completely agree, sir. Thank you very much, sir.
Thank you,
madam.
thank you. Thank you so much.
Good evening, sir. I am Dr.
And
Preeti Ranjan Sahu from NIST University, Barampur.
good evening,
evening,
Preeti
sir.
Ranjan Sahu, sir. How are you, sir?
Fine, sir.
Okay.
As cited by Sandeep, sir, we need to have a offline session for this faculty development program, because the thing is hands-on session is missing in the online program. But we got very informative session. We have seen various experts like Ramesh Bansal, sir. Thanks to you both coordinators. And Yogendra, sir, please call us for a offline session. We are eagerly waiting to meet you.
Yes, sir.
Thank
We will try next year, sir.
Thank you very much
Yeah,
for the wonderful sessions.
Online session has been just conducted to came to know how many of you are interested for the offline session. So you are good in numbers,
Sure.
definitely we
Sure,
But
sir.
आज आना सर आप फिर हम ऑफलाइन करेंगे तो आपको आना पड़ेगा सर.
हाँ, सबको आना
Sure.
पड़ेगा.
I will definitely.
Okay, thank you, sir.
Thank you so much, sir.
Welcome, sir.
Yes, so any feedback from the other participants? It was really a interactive sessions with the participants. So any more feedback from the participants, let us know. Otherwise, we'll go for the next session.
Good evening, sir. Myself,
Very good evening.
Dr. Dilip Khamari, sir, from Odisha.
How are you, sir?
Fine, sir.
Good,
Sir. Sir, actually, the session was very much interactive, and especially the two professors from Bansal sir and Kole sir, they were given their the concept that is very much helpful to us. And from Jamia Islamia University also, sir has given a fantastic methodology that will be definitely suitable for us to apply in our research work, sir. And special thanks to Arya sir and Saxena sirs and the whole team of the university. I hope in your future the program will be in blended mode, so that even if we are unable to participate in physical mode, we can have in online mode also, sir. Thank you, sir.
Okay.
Thank you so much,
Thank you very much, sir.
Sir, please.
Thank you. So any more inputs from the participants, please?
Okay.
Okay, that's fine, sir.
We can-
Kashika, I think move to the next part.
Yes, sir. Now, I would like to invite the chairperson of Electrical Engineering Department, Professor P.R. Sharma, sir, for the vote of thanks.
Thank you. Good evening to everyone.
Good evening, sir.
Good evening, sir.
It is my privilege and honor to propose the vote of thanks on behalf of Organizing Committee of the AICT sponsored Atal Faculty Development Program on Advanced Trends for Optimization, Protection and Control in Electrical Base System, held from 17th November to 22nd November 2025 in the online mode. First and foremost, I extend our heartfelt gratitude to AICT and Atal Academy for granting us the opportunity to conduct the FDP and for their continuous support and promoting quality training and professional development for the faculty across the country. My deepest appreciation goes to our distinguished speakers who have shared their rich expertise and delivered insight sessions on relevant topics. Your contribution have significantly enriched the knowledge base of participants and inspired new directions for the teaching and research. I am grateful to our Honorable Vice Chancellor, Professor Rajiv Kumar, for his constant encouragement and unwavering support in fostering academics. Sir, your vision and leadership truly guide us to aim higher in all academic and research endeavors. I sincerely thank Registrar Professor Ajay Ranga and Dean FET Professor Rajkumar for constant encouragement and support and organizing programs like this, which help in shaping the holistic development of the students. A special note of appreciation goes to our program coordinator, Dr. Abhinav Saxena and Dr. Yogendra Aryaji, faculty members and staff who worked constantly to make this program a successful. Your commitment and teamwork are the backbone of every event in the department. Lastly, my thanks to the organizing committee, volunteers, and technical team whose efforts behind the scenes have ensured today's program run smoothly. With this, we bring the Validity program to a close. Thank you all for being here and making this day memorable. Thank you very much. Thank you.
Thank you, sir. Abhinav, sir.
Oh, sorry.
Yes.
Now, I request all the participants for the last time, please switch on your camera for the group photograph. Everyone, please switch on your camera. Vinayak?
Yes, sir.
स्क्रीनशॉट ले लेना, ठीक है?
Yes, sir.
Everyone, please switch on your camera for the group photograph, please.
Yes, sir.
Okay, thank you, Vinayak. So with this, we are closing the validatory session of this 6 days AICT sponsored Atal FDP program. So once again, I'm highly thankful to all the participants for giving their continuous time beyond their working hours. So thank you so much.
I also, yes, sir, Abhinav,
yeah.
sir. I also thank the students. We help us in video recording.
Yeah. And the last and the special thanks to all the third year, second year, third year, and final year students who are supporting us from for the whole sessions from the 6 to 9. Apart from their academic work, they give their extra time to us for this successful of this online Atal FD program. So thank you, Vinayak. Thank you, Kashika. Thank you, Mehak. Thank you, all the students.
Thank you, sir.
Okay. So what will be the next?
Thank you, sir.
Yes, sir. Yeah. Sir, our next is simply a online quiz. So participants, I'm sharing the link of the online quiz on the WhatsApp group, not on this the chat box, because we are after this we are about to end this program. So I'm going to share the link of the Google form of the online quiz on the WhatsApp group, and the duration will be of 1 hour.
Yes,
okay.
I also request the participants to register their feedback in the Atal portal. After registering their feedback and after submitting the attendance by us and the marks by us, then you will be able to download your participant certificate.
Yes. So kindly note it down. This was a really important point. So you can just give your feedback on the AICT portal as a participant. Thereafter, we will submit your this attendance and marks. Then after that, you can download your this participation certificate. So thank you so much, Arya sir, for giving the information.
Okay. Thank you, sir.
Okay, fine. So I'm sharing this link on the WhatsApp group. So if you are facing any problem, please let me know. Okay. So once again, thank you everyone. Now we are about to close this ceremony and this whole sessions. Okay.
Okay.
Thank you everyone. Thank you once again.
Thank you, everyone.
Thank you, sir. Thank you, PR Sharma, sir. Thank you all the participants.
Thank you, sir.
Thank you all.
And the duration of the quiz will be 1 hour. Please just remember. After that, this link will be closed. Okay. So Vinayak, now we can close the meeting right now. And
Sure,
you can
sir.
stop the recording and close the meeting.
Okay, sir.
Okay. Thank you.